索，心里很小心翼翼。如果说细节到会触景伤情，还记得有片森林，里面住着爱情。分开后，这颗心变得多么干净。你对我多么重要，是我一直的依靠。离不开你了就好，最难过是习惯知不知道，其实你真的重要，就想陪着你到老。看时光变迁，你还在身边，这感觉真好。你对我多么重要，是很忌讳的毒药，拼了命的想戒掉，一个人的生活变得浮躁。其实你真的重要，依旧敷衍着傻笑，听一起听的歌，看一本小说，这样子最好。
不知不觉我想要他，想方法去表达，勇气你在哪？那么多路人甲，阻挡不了我对你爱的想法。抛开那些最浪漫的话，我只想为你把所有愿望融化。就这样一直走，我这一生中的每一个冬夏。
那一天遇见你，你的与众不同，就像一个天使，难以忘记那个笑容。
你的出现是我唯一的心动，我心里对你的想念充满每一天。
滴答滴答，时间在转动，滴答滴答，我希望你懂。每当闭上眼，脑海都是有你的梦。
一起欢笑，一起疯，越相处越感觉 I love you。随着习惯，像独角拥有你的快乐。
一起欢笑，一起疯，越相处越感觉 I love you。每分每秒陪伴你的苦乐。
不知不觉我想要他，想方法去表达，勇气你在哪？那么多路人甲，阻挡不了我对你爱的想法。抛开那些最浪漫的话，我只想为你把所有愿望融化。就这样一直走，我这一生中的每一个冬夏。
那一天遇见你，你的与众不同，就像一个天使，难以忘记那个笑容。
你的出现是我唯一的心动，我心里对你的想念充满每一天。
滴答滴答，时间在转动，滴答滴答，我希望你懂。每当闭上眼，脑海都是有你的梦。
一起欢笑，一起疯，越相处越感觉 I love you。随着习惯，像独角拥有你的快乐。
一起欢笑，一起疯，越相处越感觉 I love you。每分每秒陪伴你的苦乐。
不知不觉我想要他，想方法去
秋风落日入长河，江南烟雨行舟。乱世穿空卷起多少的烽火。万里山河都踏过，天下犹如谁手？分分合合不过几时在春秋。我在十面埋伏四面楚歌的时候，把酒与苍天对酌。纵然一去不回，此战又如何？谁见万箭齐发，星火漫天夜如昼，刀光剑影交错。而我枪出如龙，乾坤撼动，一笑破苍穹。长江刺破云霞，放下一生牵挂。望着汉月儒雅，孤身纵马，生死无话。风卷残骑列甲，血染万里黄沙。成败笑谈之间，与青史留下。十面埋伏四面楚歌的时候，把酒与苍天对酌。纵然一去不回，此战又如何？谁见万箭齐发，星火漫天夜如昼，刀光剑影交错。而我枪出如龙，乾坤撼动，一笑破苍穹。长江刺破云霞，放下一生牵挂。望着汉月儒雅，孤身纵马，生死无话。风卷残骑列甲，血染万里黄沙。成败笑谈之间，与青史留下。长江刺破云霞，放下一生牵挂。望着汉月儒雅，孤身纵马，生死无话。风卷残骑列甲，血染万里黄沙。笑谈间，谁能留下
？We together bet。
你出现就沉醉了世界，没有救，我像个荒诞的可怜人。可是你却不曾施舍而来，你的酒馆对我打了烊，子弹在我心头上了膛，请告诉我今后怎么看。 手上了当，请告诉我今后怎么扛，遍体鳞伤，还笑着原谅。你的酒馆对我打了烊，承诺是小孩子说的话，请告诉我今后怎么扛，你无关痛痒。请告诉我今后怎么扛，你无关痛痒。
让我们有请王力宏战队洪雨雷出战，欢迎洪雨雷演唱《流星雨》。
让我们一起去看流星雨好吗？
好。
小郎酒全国热销的小瓶白酒提醒您下节更精彩。蒙牛冠益乳提醒您精彩马上回来。增强免疫力，请喝冠益乳。蒙牛冠益乳提醒您精彩继续。喝冠益乳，助力你心中的好声音。即日起购买冠益乳，扫描包装内二维码。
沿着路灯，一个人走回家，和老朋友打电话。你那里天气好吗？有什么新闻可以当作笑话？回忆我都不爱说话，偶尔我会想起他，心里有一些牵挂，有些爱却不得不各安天涯。在夜深人静的时候，想起他送的那些话，还说过一些撕心裂肺的情话，赌一把幸福的筹码。在人来人往的街头，想起他，他现在好吗？可我没有能给你想要的回答，可是你一定要幸福啊。回忆我都不爱说话，偶尔我会想起他， 还说过一些撕心裂肺的情话，独一而幸福的筹码，在人来人往的街头响吉他，身在后马，可我没有能给你想要的回答，可是你一定要幸福啊。哦，幸福啊。
一遍、两遍、三遍的思念，那是儿时的落叶，伤口纵光的那条街，枯萎的落叶，回忆多甜，是你的脸。后来的那一天，那一年，你离开就没有见面，我真的想念，是真的想念。你呢？还记得我吗？好久不见，你好吗？多想说出那一句话，我爱你呀。只怪我当初太挣扎，挣扎后却把你丢了。现在你在我面前多么好啊！你呢？还记得我吗？我真的好想你呀，能不能抱紧我，然后就回来了？回忆那种想念，只是你不在我的身边，偷偷想念，想念不过去面。一遍、两遍、三遍的思念，那是儿时的落叶，伤口纵光的那条街，枯萎的落叶，回忆多甜，是你的脸。后来的那一天，那一年，你离开就没有见面，我真的想念，是真的想念。你呢？还记得我吗？好久不见，你好吗？多想说出那一句话，我爱你呀。只怪我当初太挣扎，挣扎后却把你丢了。现在你在我面前多么好啊！你呢？还记得我吗？我真的好想你呀，能不能抱紧我，然后就回来了？回忆那种想念，只是你不在我的身边，偷偷想念，想念不过去面。是谁的爱啊，比泪 去，这尽管慢慢好玩具。
梦想穿过了细雨，包含了多少的差异。
爱情像一本游记，我会找寻它的谜语。看月牙湾下的泪光，在丝路之上被遗忘。
是谁的信仰，孤单的留下。
他还好吗？我多想爱他，那永恒的泪凝固那一句话，
也许可能惩罚。灯光停过的山里，带着我们的记忆。
我从半路看回去，这尽管慢慢好玩具。
梦想穿过了细雨，包含了多少的差异。
爱情像一本游记，我会找寻它的谜语。看月牙湾下的泪光，在丝路之上被遗忘。
是谁的信仰，孤单的留下。
他还好吗？我多想爱他，那永恒的泪凝固那一句话，
也许可能惩罚。是谁的爱呀，比泪水坚强。
轻声呼唤，就让我融化。
每一滴雨水烟花，着我翅膀，
想着我爱的人。
是谁的信仰，孤单的留下。
他还好吗？我多想爱他，那永恒的泪凝固那一句话，
也许可能惩罚。
是谁的爱啊，比泪水坚强。轻声呼唤，就让我融化。
每一滴雨水烟花，着我翅膀，想着我爱的人。
是谁的信仰，留下？是谁的爱啊，比泪水坚强？是谁的信仰，孤单的留下？是谁的爱啊，比泪水坚强？有天我睡醒，看到我的身边没有你，在我的右边是你曾经喜欢的玩具。可当我站起身来，在房间里寻找你，留下的只有带着你味道的一封信。就在昨天还一起看我们的照片，可现在让我感觉像烂剧里的主演。为什么这种事情会发生在我身边？是不是老天没能看到对你的疯癫？还想着创造你的宇宙，但现在已经被我清空。你让我整个人都冰冻，还怎么再次对你心动？会革命不是你的意愿，离开我开始新的起点。可能我还会对你贪恋，谁让你曾经为我疯癫？抱歉，不应该假装看不见。回想这几年，我们的爱犹如病变，天天在上演崩溃的情节，直到你选择不告而别。起码现在你留下的小熊还能陪着我入眠。如果不想为你疯癫，拿来曾幸福的画面，所以不会后悔遇见。虽然爱情还是病变，想可能是怕我难过，所以忘了说再见。可怕的病变要康复需要时间，只是现在这房间还是有太多我们快乐的照片。有天我睡醒，看到我的身边没有你，在我的右边是你曾经喜欢的玩具。可当我 事情会发生在我身边？是不是老天没能看到对你的疯癫？我不能够停止啊！这些年我对你的疯癫，还会带上那条围巾吗？在每一个寒风刺骨的冬天，还有每次送你在回家的路上，不经意间又触碰你的手。我穿裙子眨眼睛望着你，那些让你心动的瞬间。那条十字路口始终有你身上的气味，车水马龙过后的路灯下的身影又会是谁？他说我真的喜欢你，可是每次欲言又闭嘴，那是荒唐的男孩又浑浊了几岁。有天我睡醒看到我的身边没有你，在我的右边是你曾经喜欢的玩具，可当我站起身来在房间里寻找你，留下的只有带着你味道的一封信。就在昨夜还一起看我们的照片，可现在让我感觉像烂剧里的主演。为什么这种事情会发生在我身边？是不是老天没能看到对你的疯癫？
我爱你，无畏人海的勇气，用尽余生的勇气，只为能靠近你，哪怕1厘米。爱上你是我落下的陷阱，不惧岁月的更替，往后的潮汐，无论风雨。
กลับมาจ้ะ
界上有很多的东西，生不带来，死不带去。你能带走的只有自己和自己的脾气。你曾拥有最美的爱情，你听过最美的旋律，触摸过一个人孤独的恐惧，也看到过最美的风景。我跌跌撞撞奔向你，你也不能一个人离去。我们在一起说过，无论如何一起经历。
Hi, good afternoon, everyone.
平平
Professor Mingye, are you be there?
Yeah, yeah. Nice to
Good
meet you.
afternoon.
Yeah. Good afternoon.
Okay. Do you need to check your slide?
Yeah.
You may share your screen
Okay.
for check your presentation. Yeah.
Okay.
Wait a moment. It's okay. And please slideshow.
Yeah.
Yeah. Please full screen.
Okay. Okay.
It's okay. It's okay. Nice.
Okay.
Okay. So wait a moment. Maybe 1 minute.
Okay.
Okay, good afternoon, everyone. Welcome back to YSCRC 2021. Today is the last day of our symposium. For the closing ceremony, we will announce the best presentation award. Now we have 5 awards supported by Holibak Scientific Company. And also we will announce the next host for YSCRC. So don't forget to join with us at the closing ceremony. For this session, Assistant Professor Dr. Surachai Kanchanakom will be a chair of this session. Please, Dr. Surachai.
Okay, thank you very much, Professor Chanati, for your kind introduction me. And maybe we can start now, Ajahn Chanati.
Yes.
Okay. Okay. Good afternoon, ladies and gentlemen. Welcome to this conference. And for the first speaker is the invited speaker for this season is Professor Mingyue Ding. He's from Wuhan University, and today he will present in the topic of the efficiency converting syngas to liquid fuel with reduced CO2 emission. Okay, please join welcoming Professor Ming Yuan for presentation. Okay, please.
Yes. Thank you. And I will introduce my work. Good afternoon, everyone. It's my pleasure to introduce our work. The topic is syngas converting to high value chemicals while suppressing CO2 by product. As we know, CO2 emission is a very bigger problem in the world, and now many countries make some measures to reduce CO2, and in China, CO2 emission is about 30% CO2 in global world. And we can find from left picture, we can find the CO2 emissions of energy structures in China. Many come from coal, oil, cement, and gas. We can find CO2 emission about 30% in coal. So the optimal utilization of fossil energy and CO2 utilization are very important in China and in the world. We can say the traditional energy such as coal, biomass, natural gas can convert it to syngas, and syngas is mainly platform. We can get many chemicals and fuels from syngas. And in China, there are two big industry equipment. One is syngas to merchant to low olefins, and the equipment capacity is over 1 million tons every year. And another pathway is syngas convert fuels such as gas or lime, diesel fuel from FT synthesis route. And today I will introduce this pathway, FT synthesis. And we can get many chemicals from FT synthesis. We can find some big progress in the fundamental research. And there are two examples. One is we can get over 80% lower olefins from syngas through oxide zeolite catalysis. And another pathway is from cobalt-based catalysis. We also get raw oils. And we found these two pathways, the CO2 selectivity is over 40%. That means it is a problem to reduce, and it is difficult to reduce CO2 byproduct. Why CO2 is reduced so difficult? We can find FT reaction. We found when we get hydrocarbons from FT reaction, we found the water reformed. When water reformed and the water CO to react to produce CO2 and hydrogen, that is famous reaction, water gas Schaefer reaction. And we can find water gas Schaefer reaction take place in FT reaction. So that is why we don't reduce CO2 percent. So if we found a new way to reduce, and I think this is very challenging. And in these years, there are some progress in some work to reduce CO2 byproduct. We can find L compact and such as arrow compact. We can find in this phase, we can suppress CO2 product at a low temperature. When the temperature increase and the CO2 byproduct increase, and from this picture we can find the CO2 conversion is lower and CO2 selectivity is lower. But when we increase the temperature, and we can find the CO2 selectivity increase. So this is very difficult for us to control the reaction. So anyway, we can find the aero carbide is only this phase can suppress CO2 byproduct. So we want to design catalysis, and we want to get only air carbide, and then on the this phase we get the hydrophobic layer and restrain the water gas shift reaction. And from this active phase, we can get many product, one phase or other product. And outside, we can restrain the side reaction, the water gas shift reaction. So we want to do this. And at first, we design a catalysis. We prepared traditional iron catalysis, and this catalysis is hydrophilic, and then we modified this catalysis, and we got hydrophobic catalysis. And this we can observe this catalysis is hydrophobic. And then we found this catalysis is only aero carbon during reaction. And the traditional iron catalysis we can find magnetite reform. So from hydrophilic catalysis, both phases were formed. For hydrophobic catalysis, only iron carbides were formed. That means we can control this phase. And from this process, we can find clearly the active phase control. When we penetrate catalysis and only aero carbides formed for two catalysis, and when these two catalysis in the FT reaction, we found this catalysis and magnetite formed. And we can find hydrophobic catalysis is only aero carbide. So we control the active phase. So when we control active phase, we can find the CO2 and the methane reduce much, and the product is only film, and the CO conversation is more than 40%, 50%. So, and this catalysis has the best perform in syngas converted to chemical. And then we continue research the mechanism of suppressing CO2 byproduct. So we can find the CO2 product can be produced from the two reactions. One is the magnetite to CO and get CO2 from this reaction. And we can find traditional catalyst, we can get this CO2 product. But from the hydrophobic catalysis and this reaction can be stopped. And then when we has hydrophobic layer on the catalysis, and this reaction is also restrained. So we can find the outside and the inside. We can find the hydrophobic layers formed outside. And we checked absorbed water and water vapor in the reaction. We can find that this catalysis has excellent performance to reduce the water absorbed. So we change the layer. We can modify the performance. And then we can find the date, and we can find the hydrogen to CO, the ratio can be reduced from this new catalysis, and the product is mainly olefins. So we can find when we in the similar level of CO conversation, the hydrophobic aerial catalysis decreased the selection of CO2 byproduct. So in the basic of our catalysis, we continue to modify the performance. We added magnetizes promote in the hydrophobic catalysis, and we can find we can get much water fields. And when we change the ratio, we can get better performance. But when we added much promote, we can find the performance decrease. So we changed. We checked when we get more promote manganese content, we can find the magnetite formed during this process. So this is why the CO2 product increase and other products negativity decrease. And when choose the best candidates, we can find the stability is better. We can find from this. We checked 100 hours. We found it is the main better performance. And then when this work produced, and many researchers and say this is a new idea to regulating aqueous reaction. We can find that when we in the traditional catalysis, water gas shift take place on the catalysis, but in our catalysis, we stop the formation of magnetite. So the water gas shift reaction is stopped. So it's only FT reaction to get on fields. And then we modified reaction and we can find that we check the synthesis classification synthesis unit, and we from modified we can get much lower cost of product. We can find the cost decrease 20% in our analysis. So looking forward, we saw the hydrophobic layer in the analysis. We can change the product. We can get more product and suppress the CO2 product. That's all. Thank you for attention.
Okay, thank you very much, Professor Mingyue, for your nice presentation. And we still have the time about 10 minutes for question and comment. We can discuss from now. Yes, Professor Guan, he asked, yes.
Yes. What from FT reaction? FT reaction, we can get water, and from this. From this reaction, we can get water, and when the water from Earth and water gas shift reaction take place. And the second problem, how do you let progress coat well on ion carbon? Yes, I think we should get better experience, and from this progress, and if you know, we can show this reaction, and we get hydrophobic analysis. Yes. Thank you.
Okay, and
sorry.
Yes, please.
Can you hear me?
Yes,
is
yes.
the coating of the silicon oxide for the ion carbon this compound is for single molecular or for several or how many molecules? Just coating as a cluster or coating as a single molecule?
Single, yes, single, yeah.
It's single. But your plot, your image is not a single. It's a gas. It's your many molecules of the ion carbon. This is ion carbon.
When we at first we got this analysis, the iron oxide, and then we changed the outside layer from this reaction. We used this chemical, and from this process we can change the hydrophobic and hydrophilic. Yes. Yeah.
Okay.
Okay, how about another one? Still have the time, 3 minutes.
So how about the cost? I mean, where this way, how does it is it more expensive than one without coating? Maybe
yes, I think we through calculation we compare this cost and yes, you can say right yes, yes, we
because
calculate
of the efficiency, okay.
Yes.
Or
yes.
okay.
Mm.
Okay.
Okay. So another question. Okay, if no one, I also interest about. I'm not sure about slide 17 or 18. I'm not sure how you control the product selectivity when you dope the MN. I'm not sure. Maybe slide 17 or 18.
Yeah.
Yeah. How you control? I mean, when you add the amount of MN increase, right? The product selectivity is changed, right? Could you explain about this phenomena?
Yes, and we can find when we add such promote, we can change the pathway from the electric path. Yes, and
Yes.
there are many many reasons in this system. So we just check the main reason for control the product, and I think in FT reaction control product we can do better. Many researchers groups can do better in control product, but CO2 is not controlled in FT reaction. That's why we must do this because CO2 is bigger problem in the world.
Yes.
Yes.
Okay. Okay, maybe the time is finished. Okay, thank you very much, Professor Mingyue Ding, for your night presentation again.
Thank you.
Okay, thank you. And we will move to the next speaker.
Yeah.
The next speaker is Miss or Mr. Yuhua Zhang. He will present about the propylene epoxidation with hydrogen and oxygen over Au zirconium oxide. Okay, please join. Welcome Yuhua Zhang for presentation.
Okay. Thanks to Honorable Chairman. Ladies and gentlemen, good afternoon. It's my pleasure to be able to attend this meeting. Today, I'd like to present my report, Propylene Epoxidation over Gold Catalysts on Zirconium. I'm from Institute of Process Engineering, Chinese Academy of Sciences. In the first part, I am going to begin with the background of propylene oxide production. These are the traditional processes for PO production. However, they are all harmful for the environment. These days, the direct propylene epoxidation is a green and sustainable reaction. This reaction exhibits different routes, including isomerization of PO and over-oxidation to CO2. So Improving the selectivity to PO is one of the research focuses of propylene epoxidation. For this reaction, almost all work was on gold catalysts using titanium-containing materials. The questions raised here, look, why titanium is necessary, whether titanium is unique for this reaction, and what the active sites or other effective non-titanium supports. In order to clarify these questions, we choose zirconium as the support as a start of our work. Originally, gold loading of 0.5% was applied to prepare gold catalysts on zirconium calcined at 4 different temperatures. These 4 samples. The reaction results are listed in Table 1. It can be seen that the product selectivity highly depends on the calcination temperature. For the case of this gold zirconium 400, only trace PO appeared and the main product is CO2. With the increase of the temperature to 800 and 1000, a decrease in the production of CO2 was observed, and we can see a considerable improvement in the selectivity of PO. For these 2 samples, PO selectivity reaches 100. This seems that the product selectivity highly depends on the calcination temperature of zirconium support. The XRD and XRD patterns and the Raman spectra can prove that with the temperature, with the increase of temperature, our samples transform from tetragonal through the mixed phase to monoclinic phases. And from this Raman spectral, we can see that for this sample, the zirconium 400, some tetragonal catalyst was embedded into the amorphous phase. The trend of the fraction of monoclinic zirconium is this order, which is in good agreement with the trend of PO selectivity. From the TEM and HRTEM images, we can see that the sizes of supports increase with the calcination temperature. The small particle size in the zirconium 400 increased chance for these gold nanoparticles to contact with multiple zirconium particles, resulting nanocomposite gold catalyst. The chemical compositions of our samples are investigated by XPS. We can see figure 4A. As the temperature was increased, the zirconium 3D peaks shifted to lower binding energy from this to this. This shift can be attributed to the progressive reduction of the zirconium or to the decrease in the coordination number of the zirconium ions. From figure 4C, we speculate that there are multiple defects in the supports, especially for the zirconium 400, as the calcination temperature is low and its crystallization is imperfect. From the results in Table 1 above, it seems that the PO selectivity highly depends on the crystal phase of the support. However, for this sample, it shows much different properties because it has low content of monoclinic. So we reduced the gold loading from the results in table 2, where the golden nominal loading is here 0.2%. The PO selectivity increased to 100. However, continue to reduce the gold loading to 0.05%. Acrolein increased to the second product. Then we raised the gold loading to 1%, and the acrolein was also produced as a second product, and the PO was increased. The above results suggest that the reaction pathway in the studied system varies with gold loading. And as listed in table 3, a similar change in product selectivity with respect to gold loadings were also obtained over gold, the Cornian 1000. And we can see that the acrolein is the main byproduct. Interesting, CO2 for this catalyst was depressed. No CO2 appeared in this sample. So on the basis of the results above, we speculate the reaction pathways for our catalyst. For PO production, the important factor is the Cornian oxygen rectangular pyramids. For acrolein, the important factor is the oxygen defect. Oh, okay. So in summary, we use the Cornian as a support for propylene application, and we get the 100% PO selectivity, which is the first time reported on this reaction. Okay, that's all. Thank you.
Okay, thank you very much, Ms. Chang. And we still have 1 minute for the question and comment. Anyone has the question, comment, please? Still have time, 1 minute.
Okay, please.
Yes, please, Professor.
Is there any other researchers in China working on this?
There are some people work on this. There are very few workers focus on this reaction now because it's very it's difficult to raise the selectivity and the propylene conversion. Huang Jiahui, I don't know, from 大连话务所, I don't know how to.
Yes, I know. Yeah. Please work on this. Okay. But you said that you get the 100% PO selectivity. Did you repeat this experiment? Or
yes.
How about the range, the condition range? I think if this result is valid in a range of conditions, that makes sense.
The PO selectivity can reach 100%, but the conversion of propylene is very low. So
okay, that's you needed to do more work. Yeah.
Yes, it's just a basic focus on the basic research.
Okay.
Good.
Okay. Maybe the time is finished. Okay. Thank you very much for your nice
Well,
presentation.
good presentation. Good.
Thank you. And we will move to the next speaker. The next speaker is Wasipim Chan Seliwat. He's from Khon Kaen University. He will present about the oxygenation of palm oil to light biofuel over calcium-based catalyst released from the gypsum waste under atmospheric pressure. Please welcome presenter.
Can everyone hear me?
Yes.
Okay. And everything is okay, right? Okay.
Maybe can you share full slide?
This is full slide. Is it full now?
Not yet.
This is.
Yeah.
Yeah. Okay. It's a bit delay, so okay. Good evening, everyone. I'm Wasipim from Khon Kaen University. Today, I would like to present a part of my thesis entitled of the oxidation of palm oil to light biofuel over calcium-based catalyst derived from gypsum waste under atmospheric pressure. Nowadays, we are facing global warming. The global temperature rises up every year. So, to reduce the temperature, we need to find a way to reduce carbon dioxide reduction. There are many ways to reduce the carbon dioxide. The one way is very popular nowadays is to use renewable resources, including solar power, hydropower, wind power, or biofuel. Moreover, Thailand produce palm oil about 2 million tons a year to utilize the domestic product. We came up with the idea to produce the biofuel by palm oil. The process that can use for producing the biofuel from palm oil is pyrolysis process. This process is really cheap and simple and don't need any assistance to proceed. That's why we show the pyrolysis process. Anyway, pyrolysis process can use with many types of catalysts, including the acid catalyst or base catalyst. But for producing the biofuel from palm oil, base catalyst is better because it can reduce the acidity in bio oil. So our tips are: the first one, to study the biofuel production by catalytic pyrolysis of palm oil using calcium oxide, magnesium oxide as a catalyst derived from synthetic gypsum via a packed bed reactor with different reaction temperature. And the second one is to study the effect of variant magnesium percentages. Is everything okay?
Yes.
Okay.
Okay.
The first part, I would like to present about my experimental part. The first step, we need to synthesize the calcium hydroxide first, and then we show the gypsum as the raw material because gypsum is abundant waste in Thailand. more coal power plant produce some as a product about 1 million ton a year. So translating it to the calcium hydroxide. After we got the calcium hydroxide, we need to mix it with the magnesium carbonate and bentonite. The amount of magnesium carbonate is controlled by the magnesium percentages that we want to make the catalyst. So we each percentage of magnesium was controlled by amount of magnesium carbonate.
Hello, Miss Wasipim. Maybe the internet has some problem.
Maybe her is some technical problems. We may skip to next presenter. If she back, she will present again.
Oh, she already back.
Already back, right?
Yeah.
Okay, so she can continue.
Okay.
Okay. I'm so sorry. Okay.
So now we cannot see your slide. I'm not sure, maybe about your internet.
Okay.
Signal.
It's on. Yeah, the signal is, yeah, maybe it's a signal, but you can see my face, right?
Yeah.
No.
So now we can see your slide also. Oh.
So we may skip. We may skip.
Okay. So we will skip to the next speaker, Ajahn Chanatip.
Yes.
Okay. So let's move to the next speaker. Miss Tanyalat from Thammasat University. She will present about preparation of epoxy palm oil and application as rubber processing oil. Okay, please Joy, welcome for presentation, please.
Did you see? Did you see my screen? Right.
Not yet. Maybe you have to share first.
Okay. Did you see my screen?
Yeah. We see your slide now. Okay, please.
Good afternoon, everyone. My name is Tanyalat Phakeo. Today, I would like to present in my research topic preparation of epoxidized palm oil and application as a rubber processing. Oil is additive for rubber processing because the oil will reduce viscosity of rubber compound in the mixing process. Moreover, it also promoted vulcanized rubber to have better quality. But the rubber oil that are commonly used is derived from petroleum base, or we know as mineral oil, because it's cheap and they have features that can be matched with variety of rubber. However, the majority of mineral oil on the market contain hydrocarbon molecule with numerous aromatic links. It's classified as a carcinogen substance with cytotoxic or mutagenic effect, and also effect to the environment.
Epoxidation reaction is an oxygenation reaction using acidic substance. In the first step, the acid will react with hydrogen peroxide solution to form peroxide, and the acid in the form of peroxide will react with the double bond again to form an epoxide ring. In this reaction, byproduct is water, and remaining acid can react with epoxide ring to form other substance, which will cause the epoxide ring to decrease. Adding epoxidized palm oil to the rubber production process, it will help the one-cannite rubber to be more soft for easier forming and also enhance the tensile state property. So this has led to interest in the study of epoxidized palm oil as an alternative to existing mineral oil and resolving the problem of environmental toxicity from the production process. So the objective of this work was to study the process of improving the property of palm oil by epoxidation reaction at the following scope of study. First, study on the influence of amount of catalytic concentration. Second, study on the influence of temperature. Third, study of the influence of duration time, and the last one is study of influence type of acid between acetic acid and formic acid method. In the experiment, we'll divide it into two parts following like this scheme. First, we weigh palm oil before adding gaseous acid and gradually increase heat to the set temperature, and then add sulfuric acid and stirring for another 5 minutes before adding hydrogen peroxide. At the end of the reaction, we will stop the reaction by cooling and neutralize the pH to about 7 with deionized water, sodium hydrogen carbonate, and sodium chloride solution respectively before being centrifuged and evaporation water with rotary evaporation. And after we got product, we will take to property testing to study the influence of catalytic concentration. From the experimental result, as shown in the table, it was found that percent oxygen relative conversion and percent epoxidation increase related with higher sulfuric acid concentration increase, which can be confirmed again by effect of lower iodine value with increased sulfuric acid concentration. And when considered in our result, at position 2.9 and 3.1 ppm, which are positions indicating epoxy functional group, from the result demonstrate that if used catalytic in high amount concentration, this will encourage the double bond to become more epoxide. But when we consider the physical characteristic of the reaction that using 1.13% weight by weight sulfuric acid, we got a white wax precipitate. However, it gives a relatively high percent oxygen relative conversion and percent epoxidation, even though the physical characteristics that are unsuitable for rubber processing. Therefore, it is necessary to study in other conditions. To study the effect of the temperature that influence to epoxidation reaction, the results show that at temperature above 55 Celsius degrees C, the physical characteristics were changed into white wax. It can be concluded that increasing the reaction temperature will accelerate the rate of formation of epoxy functional group in the product. Therefore, epoxidation at low temperature produce epoxy rings that are more stable than high temperature. To study effect of duration time from the result, it was found that percent oxygen relative conversion and percent epoxidation increase as the reaction time increase. This one indicates that if reaction time increase, the double bond position of triglyceride can become more epoxy as well. When considered as the physical characteristics, it was found that from the reaction time of 3 hours and 4 hours, the percentage of oxygen quite high, but they gave product apparent into white wax. On the other hand, at the reaction time of 1.5 and 2 hours, gave better physical characteristics. Therefore, 1/2 and 2 hours are suitable for epoxidation in case of percent oxygen and physical appearance. In this slide is comparison between type of acid, of acetic acid and formic acid, which have influenced on the epoxidation. And from the experiment show that both of acetic acid and formic acid method provide relatively high similar percent oxidant oxygen. And when considered MR result, formic acid provide higher intensity value than using acetic acid. However, if considering physical appearance, acetic acid should be chosen in case of application manufacturing require liquid physical appearance. For this slide, it shows physical property of epoxidized palm oil comparison with palm olein. For the result of oxidation stability of epoxidized palm oil is higher than palm olein. Therefore, reducing the double bond content of the oil by epoxidation contribute to increase the oxidation stability of the oil. And for density property, from the result is what found that epoxidized palm oil density was pretty close to palm olein, but tend to gradually decrease because the double bond in the structure become into epoxy functional group. And for viscosity property, the viscosity of palm olein is lower than epoxidized palm oil because the viscosity depends on the number of double bond in the structure. Then when calculate of viscosity index, they show the high index and a relatively high little change in viscosity during temperature change. So this is a good indicator that if is suitable for application in a wide temperature range. For pour-point property, the result of epoxidized palm oil had a slightly higher than palm olein. This is because decrease of double bond in the oil structure, they significantly decrease of pour-point. And for the acid value, from the result is what found that the acid value of epoxidized palm oil is higher than palm olein, but tend to decrease gradually according to reaction time. This one is due to the fact of triglycerides are highly hydrolyzed into free fatty acid that will affect high acidity and the impact of quality solid of oil as well. In conclusion, from the study have shown type of acetic acid method is more responsive than the formic acid method if the application requires oil in a liquid physical appearance. And for amount of catalytic concentration that are suitable for the epoxidation reaction is concentration of sulfuric acid of 1.13% weight by weight at 55 Celsius degrees C, and duration time can be synthesized at both 1.5 and 2 hours. However, when analyzing property of epoxidized palm oil comparison with palm olein, it was found that the property of the epoxidized oil were improved, but still have some defect of this work is use homogeneous catalyst that increasing step in neutralite, which use a lot of solution and several time for neutralite. And finally, I would like to thank Associate Professor Suwadikong Parakun, my supervisor, and everyone that he consult to me. Thank you for your attention.
Okay, thank you very much, Ms. Thanyaraj, for your nice presentation. And we still have the time for question and comment 1 minute. Please.
I have one short question. Okay, one question from the chat box. Please start from them. That is okay for me.
Yes, one chat from Ms. Jarianan. Can you see it?
This one.
No, she asked you in chat. Maybe I can ask you.
Okay.
But the result of the formic acid experiment show that the resulting wax cannot be reused in the rubber compound processing or not?
It doesn't mean wax that can be used. It can be used in the same way, but it requires heating step before being to mixing with rubber process. Which increase both of cost and time if considered in economic feasibility. That's why we want oil in liquid form.
Okay. Okay, maybe the time. Ajahn Shanatip, do you have question?
I have a question about in slide number 15. Yes, about the total acid number when you increase to 4 hours. Why the acid number is decreased rapidly from 3 hours to 4 hours? What happened there?
Because it go to epoxidation reaction. At first they have double bond, and when they go to epoxidation, the double bond is in structure of triglyceride is decreased, and that's why fatty acid is decreased.
So you mean the acid number represent the fatty acid, right? Or number of oxidant ring?
Sorry again.
I mean acid number is represent the fatty acid, right?
Yes.
Okay. So what happened about in the fatty acid at 4 hours?
It's decreased.
Yeah, it decreased. Why? It changed to some.
Because it used long time of duration in epoxidation, and it have a double bond is changed to epoxide ring as much because they use long time, they use time a lot of reaction.
So you mean the overreaction, right? Okay, thank you.
Okay, thank you very much, Miss Tanyalat, for your nice presentation. And we will move to the next speaker. Oh, okay, the next speaker is me. Yeah, just a moment.
So I will introduce for you Dr. Surachai.
Okay, thank you very much.
Okay, the next speaker is Dr. Assistant Professor Surachai Kanchanakom from Langsit University. He will present in the title phase production of biofuel additive ethyl levolinase from conversion of free alcohol promoted by acid catalyst with oxygen environment. Please, Dr. Surachai.
Okay, thank you very much, Professor Shanatif, for your kind introduction me. And good afternoon, ladies and gentlemen. This is nice to meet all of you here. My name is Surachai Kanchanakom. I will present my research with the topic of factual production of the biofuel additive ethyl levolinase from conversion of the furfural promoted by acid catalyst with oxygen environment. And the content for today consists of 5 parts. And the first of all is the introduction. As you know that the ethyl levolinase can be produced from the many kind of the biomass, and also the biomass can be produced into the some value-added chemical. And also in this work, we interest to produce this kind of chemical ethyl levolinase, or we can say EL. And interestingly, this we will produce from the furfural because the furfural is the cheap and more available, and also we can control the reaction pathway. And the problem is when we want to produce this kind of chemical from the furfural conversion with the one-pot step, it requires the high temperature and long reaction time, and also high pressure also. And in this case, it's difficult to be converted into the ethyl levolinase, but it will convert next step to the human. So that's why the yield, how to say that the higher yield, about 90%, cannot be achieved. So in this work, we solve that problem by using the ultrasonic reaction. So this is how to say, like promote the faster reaction rate, and also we can get the high yield and the product selectivity that we want. That like in this work we would like to get the ELU, and also can get the long-term stability of the catalyst. And also even we already achieved about that problem, but the next challenge is we would like to, how to say, like we would like to reduce about the human deposition on the catalyst, because this is the big problem that let our catalyst cannot be reused in several cycles. So in our challenge, we try to find a new way to improve the reaction and also improve the catalyst and also reduce the humid amount on the catalyst and also humid amount in the liquid product. And we try to feed the intro about the oxygen and compare with the nitrogen, and we find that the oxygen can promote the oxidative degradation during the reaction. So it means during the reaction, human formation was suppressed by introduction of the oxygen. And okay, so we will see in the result in the next slide. And the objective for this research is to investigate the physical property of the catalyst, and second, to improve the selectivity for the EL production using the ultrasound with the oxygen introduction, and to study the chemical distribution derived from the furfural based on adjusting the catalyst type. In case of the catalyst type, we will vary the different the acidity of the catalyst, and using and also the ultrasonic application, we will vary about the ultrasonic power. And the last is to study the effect of the human deposition on the catalyst. And we would like to let you see about the difference between using the oxygen and nitrogen environment, and also check with the catalyst reusability result also. And the next section is experimental section. For this section, we will prepare the catalyst first and show you about this slide. And we will add the aluminum nitrate, nickel nitrate, urea, and CTAP. And urea is for the support precipitant, and CTAP is for control the pore size, mesopolar structure of the catalyst. And during we add all in here and stir until become clear solution, and then we add into the autoclave and let hydrothermal condition at 150 for 20 hours, and then we will get the white powder product. And after that, we will calcine at this temperature for 2 hours to remove the template and also convert the boiling it into the nickel and aluminum oxide support. And actually, this is even I'm called support, but during reaction it also require the luric acid site. So this one not only support but also used as the catalyst. And the next step after we get the support, we would like to functional the sulfonic on the surface of this kind of support. So we use the reflux acid doping funnel system, and we add the support, and Ca is a chlorosulfonic acid. This is we use for the functional sulfonic group on the surface. And during reaction, it will release about the acid. And after finished functional life process, we will separate by centrifuge and then wash and dye. This is the simple method. And after we get the product, you will see from here, this is the abbreviation name of catalyst that we use. You will see 0, 1, 2, 3, and 4. And this is about the weight ratio of the Ca. Ca is a chlorosulfonic to support. You will see from here at this ratio. And for this side, this is the catalytic experiment. This is our condition. We will use the furfural 5 gram and ethanol 100 milliliter and catalyst amount at this gram. And the reaction time and the temperature we will fix since we find this is we find from our preliminary study. This is the optimum condition at 90 minutes, and the reaction time is 120 degrees Celsius. For the ultrasonic power, we will vary from 0 to 100 watt. That's it. Mean we will compare with the conventional Stirling method also. And below is a chemical product. You will see this is because for the product selectivity, I will use the abbreviation name like furfural FF, furfuryl alcohol is the FA, ethyl furfuryl ether is the EFE, ethyl rivulinate is the EL, and gamma veloacetone is the GVL, and dimethoxymethyl furfural we will use DTMF. So we will use for our result and discussion. And after we get the product, we will analyze by using the GCMS. And this is the result for the catalyst characterization. You will see from the table 1, this is the physical chemical property of different catalysts that we vary about the different amount of the chlorosulfonic. This is general trend when we increase the chlorosulfonic on the surface of support. The surface area, pore volume, and the pore size will be decreased to some extent, and also the acidity also increase. And we will use our catalyst to for the catalytic conversion of the furfural into the ethyl rivulinate. And the below one, this is the best catalyst that we choose, and I would like to show you about this is the difference. This is after the catalytic test under the oxygen environment. A is under the oxygen environment, and B is under the nitrogen environment. You will see that this is totally different. For the acidity, actually for the acidity is not significant different, because during reaction just small amount of acid is leaching, but the problem is the humin deposition on the catalyst. So that's why the surface area is decreased highly. And when you compare between the A and B1, you will see right in nitrogen environment, the surface area is decreased a lot when compared with the A1 using the oxygen environment. And also we will show you about the next slide for the catalytic test. And for the below one is the figure 1 is the XRD pattern of the catalyst. This is just confirm that when we synthesize the catalyst by using the hydrothermal method, using the C-tab as the template, we get the pore size is a mesoporous structure, and also get the hexagonal structure as well, confirmed by the XRD. And also we also confirm by the Y angle, also show that the pattern is corresponding with the gamma alumina. And for the nickel oxide, because when we calcination, we will get the aluminum oxide and also nickel oxide. But in case of nickel oxide, we cannot see because we use just very small amount. If we use too much, it will not be homogeneous when we see from the SEM. So that's why we have to fix just small amount, and we cannot see because it's just small amount like homogeneous. And this is my result. You will see for the first one is the effect of catalyst type. You will see in case without using catalyst, we cannot get the product of the EL, because actually the FF conversion can convert, but how to say it convert into the DTMF, or that's it mean the ultrasonic also promote the FF conversion, but it's shipped to the side product. And after we use the catalyst, you will see even we use the support, but we cannot get the ELU because it is just convert from the furfural into the furfuryl alcohol via the hydrogenation reaction because it requires the lewis acid catalyst. But after we intro about the sulfonic acid, you will see, right, the ELU is increased sharply, and we get the best one is this catalyst number 3, and for the number 4 is the yield of EL is decreased because it promote the second hydrogenation to convert into the humine and the gamma veloacetone. You will see from this product selectivity. So we will choose the catalyst number 3 is the best for use to the next slide. And for this slide, we will vary about the effect of the ultrasonic. You will see from here, if we increase the ultrasonic power, the percent of EL is increased sharply, and we get the maximum at 81. And in case without using the ultrasonic, we get just small amount. That's it mean. Even we use our catalyst, but it also require high temperature, long reaction time.
Dr. Surachai, now is a time up. Please summarize your
I
work.
will summarize to this slide. Okay, and for this slide, I just show you about the interestingly is when we use the nitrogen and oxygen, you will see this is we use spent catalyst and continue to continue in my reaction, and then after finish in each reaction time, we will analyze by using the TGA, and you will see from here the nitrogen, when we use the nitrogen, the humine amount is increased, and the humine, when we using the oxygen, the humine amount is decreased. This is the difference. Doesn't mean the oxygen is promote well about the oxidative degradation, and this is the corresponding with the TGA result. Okay, and this is confirmed by reusability. You will see the oxygen is the catalyst show the long-term stability, but in case of nitrogen environment, the catalyst is decreased to some extent. This is because from the humine, surely. Okay, and this is my acknowledgement, and that's all for my presentation. Thank you very much for your attention.
Thank you, Dr. Surachai, for your nice presentation. Now it's time up. If you have any question, please read the message in the chat box. So we are going to the next presenter.
The next presenter. Okay, for I have to stop sharing first. Okay, for the next presenter is Priyapan. She's from Thammasat University. Today she will present the research with the title of the modification of the superhydrophobic on the cellulose paper surface for oil and water separation. So please.
Thank you for your kind introduction. And good afternoon, everyone. My name is Priyapan Kyo-in from Thammasat University. Today, I would like to talk about modification of superhydrophobic on cellulose paper surface for oil-water separation. And this slide shows the content for presentation today. And let's start in the first part. Nowadays, oil consuming tend to increase, and oily wastewater is going to be global issue. The main cause of oily wastewater are industrial wastewater, accidental transportation, and leaking pipeline. So it so directly affect to the human and natural environment, especially endangering aquatic resource, human and animal health. And several treatment methods to separate oil from water include flotation, coagulation, oxidation process, electrochemical treatment, and membrane separation. But there are, along with secondary pollution of water, high energy consumption, high cost, and long residence time. So the membrane separation was integrated in oil water separation due to its was less pollution, less energy consumption, low cost. Moreover, surface variability had a get important role for oil water separation with different wetting behavior, including hydrophilic and hydrophobic surface. Cellulose-based material have been widely used in oil water separation application due to the presence of hydroxyl group make it hydrophilic nature and their unique properties such as natural pore that created by microfiber with excellent property including good wettability and high absorption capacity. And cellulose paper can be renewable and biodegradable. SIP8 are attractive property include large pore size, high surface area, and selective uptake of small molecule. Typically, fluoroalkyl is a low surface energy material owing to the fluoroalkyl group that show the hydrophobic property. So the composite of SIP8 and fat were used for create the superhydrophobic surface by using the spray coating method because it can be used in wide range of coating material, variety of substrate material, reduce cost and time, and appropriate for large area fabrication to construct the superhydrophobic surface on cellulose paper. And for the scope of the research, first synthesis of SIP8 particle, and then preparation of superhydrophobic surface by spray coating technique. And finally, the coated paper was used for application for oil water separation. For the experimental part, start with synthesis of SIP8 particle. First, zinc nitrate hexahydrate solution will mix with methyl imidazole solution and then stir for 30 minutes at room temperature. After that, hydrothermal reacted at 70 degrees C for 24 hours, then wash and dye to obtain the SIP8 particle. Next is preparation of superhydrophobic surface by spray coating technique. First, fast solution were dissolved in ethanol and stirred for 2 hours to obtain the homogeneous mixture. And then SIP8 particles were added and sonicated for 30 minutes to obtain the homogeneous solution that is a fatty SIP8 solution. Then the solution put in the spray gun to spray the solution over the substrate to obtain the fatty SIP8 coated on the cellulose paper. For oil water separation part, in the figure 1 show the illustration of oil water separation process that use the filter. And for separation efficiency, calculate by mass of oil collected and mass of water. And in this work, we use the 5 different types of oil, including hexane, dodecane, toluene, gasohol, and diesel. For that different in viscosity and surface tension for oil water separation test. The next part is result and discussion part. For the first is synthesis of SIP8 particle. The particle of SIP8 was 2.4 micrometer and display the petal shape as seen in the SEM image in figure C and D. And for XRD analysis were performed to investigate the crystal structure of SIP8, and the peak at 2 theta confirmed that SIP8 was successful synthesis by hydrothermal method in water-based synthesis. For SEM image of coated and uncoated cellulose paper can be observed in the figure 3. For uncoated cellulose paper, we can observe clear and smooth microfiber surface after coated with zip egg and fatty zip egg in figure B and C. We can observe that the particle disperse on the fiber surface and show the lab surface. For TM image shown in the figure 4, the morphology of zip egg particles are balanced chain after modified with fatty, indicating that fatty has no effect to zip particle. For FTIR spectra were determined to confirm the composition of uncoated and coated paper. For zip egg coated, there are two characteristic peaks of imidazole link, including C double bond N and CN, and the peak of OH stretching and OH bending confirm the existence of hydroxyl group in cellulose paper. Moreover, absorption peak of C double bond N in zip egg will disappear in fatty zip egg coated, confirming that fatty was successfully coated on zip egg particle. Water and oil contact angle were measured to investigate the surface wettability shown in the figure 6. And for figure A and B, show that low water contact angle of uncoated and coated with zip egg. And after coated with fatty zip egg, the water contact angle was increased to 150 degrees that exhibit the superhydrophobic property. Moreover, in the figure 7, show the effect of the spraying spraying cycle. From the result and increase the coating cycle was increase the surface roughness. On the other hand, in the orange color show the oil contact angle was measured by oil droplet that quickly spread on the coated surface and exhibit the oleophilic property. For the surface roughness value that of uncoated and coated paper surface shown in table 2. For uncoated paper is 3.7 micrometer, and after coated with zip egg and fatty zip egg at 1, 5, and 10 cycle of spraying cycle, the roughness value are increased with increase the cycle of spraying because an increase the helical structure over the surface that can be observed in the topology in figure A. The harmonic mean is used to calculate the surface free energy of material by the contact angle. From the harmonic mean, uncoated paper and zip egg coated paper each show high total surface free energy owing to the presence of the hydroxyl group that are polar component and zip egg that synthesized in aqueous solution. And however, after fatty zip egg coated on the cellulose paper has low total surface free energy and low polar component owing to the terminal group of fatty.
Ms. Priyapan, now the time is over. Can you summarize your research?
Okay. For the last part is oil water separation part. For the separation efficiency of 5 types of oil up to 80% and slightly different in different types of oil due to the different viscosity and surface tension. So for the conclusion part, the superhydrophobic composite successfully coated by low surface free energy of fluoroalkylsilane and high surface roughness of zip egg on cellulose paper by spray coating technique. Moreover, the fatty zip egg coated on the cellulose paper exhibit the superhydrophobic surface and show excellent oil water separation efficiency. And that's all of my presentation. And finally, I would like to thank my advisors, Associate Professor Dr. Suwadi Kongpalakul, and thank you for your kind attention.
Okay, thank you very much, Ms. Priyapan, for your nice presentation. And can you answer the question from the chat?
Yes.
Can you see it? How about the bonding performance between the particle and the fiber? Is the particle easier to separate from the fiber when the fiber was curly?
The bonding for the bonding between the particle with cellulose paper, it like a physical bonding that physical interacting, not chemical bonding. So easy to separate the particle easy to separate from the fiber. That for separation part we can use for one cycle. We cannot recycle the paper that for reuse the paper for oil with water separation.
Okay, maybe the time now is over. Maybe if you have some question, maybe you can discuss later, and we will move. Okay, thank you very much, Ms. Priyapan. Okay, and then we will move to the next speaker. The next speaker is Ms. Quen Chu. She's from Taiyuan University of Technology. She will present about the pervaporation, removal of pyridine from silent pyridine water effluent using the PEBA 2533 membrane experimental and simulation. Okay, please.
Okay, can you hear clearly?
Yes.
Okay, thank you. Good afternoon, everyone. I'm Qian Xu from Taiyuan University of Technology. The title of my report is Pervaporation Removal of Pyridine from Saline Pyridine and Water Effluent using HEPA 2533 membrane experimental and simulation. There are 3 parts in my report. First, I'd like to introduce the pyridine. Pyridine, as one of the most important organic compounds, has been widely used in the manufacture of different pharmaceutical compounds, pesticides, paints, and so on. Then a large amount of effluent containing pyridine is also produced inactively. However, the release of pyridine into the environment would do harm to the ecosystem and human because it is toxic and harmful. Thus, it is important to recover pyridine from the wastewater, which is both beneficial to the environment and economic value. However, it is difficult to recycle pyridine from the solution. On the one hand, pyridine and water would form an azeotrope. On the other hand, the pyridine presents in the effluent at a low concentration, which makes the recovery of pyridine face a health challenge. There are many techniques for recovering pyridine from wastewater, such as adsorption and extractive distillation. As a green membrane separation technique for separating liquid mixtures, pervaporation could reduce 50 to 70% energy consumption in many cases as compared to the traditional separation processes. The experimental setup of pervaporation is shown in the figure 1, and the principle of pervaporation is actually dissolution and diffusion mixing. As a membrane technology, the properties of the membrane material determine its separation performance during the pervaporation process. The solubility parameters of common organic membrane materials and permeance are displayed in the table 1. The solubility parameters of HEPA 2533 is closer to pyridine, meaning that HEPA 2533 possesses better selectivity to pyridine according to the dissolved principle. And what's more, at present, most studies on evaporation are based on binary systems, but the actual mixture system is multiple, which often contains a small amount of inorganic salt. The presence of inorganic salt can affect evaporation performance. So it is very important to study the influence of inorganic salt on evaporation process. The following are the results and discussion. First, the swelling degree of the membrane could provide a quantitative indication of the membrane affinity. As figure 2a shows, when the concentration of pyridine in the feed solution was 0, the mass of pTA-2533 remained basically constant before and after sorption, which indicated that there was negligible sorption of water in the pTA-2533 membrane. Further, the degree of swelling increased with the improvement of pyridine concentration, suggesting that the pTA-2533 had excellent affinity with pyridine. The results from the figure 2b displayed that the salt can improve the sorption of the pTA-2533. In addition, the results of the simulation showed that the addition of inorganic salt was beneficial to the separation of pyridine from water. Then the evaporation performance was investigated in the binary system. The variation of flux and separation factor, various feed composition of pyridine and water mixtures through pTA-2533 membranes was shown in the figure 4. As can be seen from the figure 4a, the water flux physically maintained invariably with the improvement of the concentration of pyridine in the feed solution. The total flux and the pyridine flux increased with the improvement of the pyridine concentration, but the increased amplitude was less than the properties in the feed solution, leading to the decrease of the separation factor. With the increase of the pyridine concentration in the feed solution, the permission concentration of pyridine increased. It can be seen that the concentration of pyridine in the permitting set was much higher than that of vapor-liquid equilibrium, indicating that the evaporation broke the vapor-liquid equilibrium, which also showed that the evaporation possessed better efficiency than distillation. On the basis of the binary system, the sodium chloride was added to the feed solution as a respective to investigate the salt effect. On the evaporation performance, we can get the flux decreased first and then increased with the concentration of the sodium chloride increasing, which took 3% as the inflection. Furthermore, the separation factor increased with the sodium chloride concentration increasing. What's more, it can be seen in the figure 6b and figure 7 that the evaporation performance has been greatly improved under the existence of the salt. As can be seen from the figure 8a and b, the pTA-2533 membrane had a dense structure and uniform thickness before and after the experiment. Further enlargement of the sectional wheel was shown in the figure 8c and d. It can be seen that there were many homogeneous particles inside the membrane, which indicated that the sodium chloride accumulating in the interior of the membrane. This was due to the inorganic salt entered into the membrane together with the pyridine and water. Pyridine and water, and then the pyridine and water evaporated on account of the high vacuum on the permitting side, while the inorganic side couldn't exist in the gas, so it remained in the interior of the membrane. What's more, the molecular dynamics simulation was performed in this study, and it could provide a useful insight into the effects of inorganic salt on evaporation that are unavailable from experiments alone. The distribution diagrams of permitting and water in solution simulated by molecular dynamics simulation software was shown in the figure 10. After several simulations, the results were averaged and recorded in table 2. By comparing the number of hydrogen bonds between water and pyridine before and after adding the sodium chloride, it can be concluded that the number of hydrogen bonds declined after adding the sodium chloride. As a result, the connection between pyridine and water became weaker after adding the salt so as to improve the separation factor. Then the effect of temperature was also studied, as shown in the figure 11a. By comparing the permission fluxes at different temperatures, it can be concluded that the higher the temperature, the greater the permission flux. What's more, figure 12 displayed log. Figure 12 displayed the logarithmic plot of total flux and partial fluxes reciprocal to temperature. The activation energy and the activation energy of pyridine and water was shown in the table 4, which was calculated from the slope of the line in figure 12 according to the apparent activation energy data in table 4. It could be concluded that the permission activation energy of pyridine was greater than that of water, and it led to the improvement of separation factor with temperature increasing. Finally, we can get the conclusion that the PIPA 2533 membrane has excellent selectivity to pyridine. What's more, the inorganic set promoted the evaporation performance, and the number of hydrogen bonds between water and pyridine declined after adding the sodium chloride. In a word, the effects of inorganic set and operating conditions on evaporation was studied in detail, and it is expected to get the design of parameters for the pyridine recovery from actual effluent by evaporation. Thank you for your listening.
Okay, thank you very much for your nice presentation. It is very interesting, and the time is near. Anyone have any question or comment? Okay, maybe because the time now is already up. Okay, thank you very much.
Okay, thank you,
Mr. Su, for your nice presentation. And now we will move to the next speaker. Is Mr. Jie Qiao from the Taiyuan University of Technology. He will present about the three-dimensional theoretic imidazole framework. It derived nitrogen doped carbon for electrochemically selective separation of the chloride ions. So please.
Can you hear me? Can you hear me?
Yeah. We hear you.
Okay.
Can you show the full slide? Yeah.
Hello everyone. I'm Qiao Jie from the School of Chemistry and Chemical Engineering, Taiyuan University of Technology. The topic of my report today is the three-dimensional derived nitrogen doped carbon for electrochemically selective separation of chloride ions. Next, I will introduce it from 4 aspects. The first is the research background. As a common corrosive chloride not only accelerates the corrosion of pipes and devices, but also threatens aquatic organisms, damages the ecosystem, and endangers human health in serious cases. Therefore, the removal of chlorine ions from chlorine-containing wastewater can increase the real rate of industrial wastewater and relieve the price of water shortage in China. Therefore, the concentration of chlorine ions must be controlled. The removal methods of chlorine ions include an exchange method, chemical precipitation, absorption, and electrodialysis. However, they generally have the disadvantages of either secondary pollution, unfriendly environment, and difficult to separate low concentration. Electrochemically switch and exchange technology adopted by our research group is an environmental design and separation technique, and the reversible uptake and release of the target ions can be achieved by modulating the redox state of EX film. It has the advantages of trace removal, no secondary pollution, controllable rate, and high selective. And the heart of ESX is ESX materials, which requires the ability to transfer electrons and ions. Here is my research idea. MOF is a kind of organic hybrid material with intermolecular formed by self-assemble of organic reagents and inorganic metal ions or metal ions clustered through coordinational bonds. The characteristics of MOF are adjustable operators, high specific surface area, uniform structures. However, its poor conductive and stability for electrically controlled ion exchange. So can we take advantage of that and use it for electrically controlled ion exchange? By simple combination, it not only retains the large specific surface area and the parent structure of MOF, but also relays heat or atomic doping, providing isolate, conductive, and stability. The activated nanoporous carbon was first synthesized by standing aging method, then carbonized at different temperatures in a tubular furnace, and finally activated by potassium hydroxide. First one shows same images of as prepared zinc MOF and carbonized sample, as you can see from the picture in the middle. After the carbonization and acid treatment from removal of zinc. The nanoporous carbon retained inherent morphology and uniform size. After further heat treatment with potassium hydroxide that form activation process, the particle size was slightly reduced and the surface became relatively rough due to the etching of carbon arisen from the reaction of carbon and potassium hydroxide. It is observed in nanoporous carbon like and active carbon that two broad peaks without any metallic peak are and 26 and 44, indicating the lattice plane of 002 and 101. The relatively weak peak of activity nanoporous carbon is much lower degree of graphic ordering result from a
Sorry, we cannot hear you. Can you hear me?
Yes, I can.
Okay, and so Miss Jia Qiao, we cannot hear your presentation. Hello.
Hello. She still be there. Hello, can you hear me?
She still but cannot. Hello, Miss Jia Qiao, you still here? Yes, because just now we cannot hear from your presentation. Is this finished?
Yes.
Oh, okay. Ajahn Chanatip, so we can move to the next speaker, right?
So, and then any question? Or we still have a question and answer? No? We still have time or not?
So now the time is already up. Yeah.
Okay, so we move to next speaker.
Okay, we still have the last speaker for this season. Welcome back, Miss Wasipim Chansiriwat from Konkan University. So she will present her topic again because maybe some problem from the internet connection. So please.
Can everyone hear me clearly?
Yes.
And can everyone see my slide clearly?
Yeah, sure.
Okay. Okay. Every problem is proved right now. So, good evening again. I'm Wasipim from Konkan University. Oh, sorry. Oh, okay. Today I would like to present a part of my thesis entitled of biofuel production from basic catalysts derived from gypsum waste collected from mammal coal power plant. Is everything clear, right? Okay. Nowadays we are facing global warming. Global temperature rise up every year. So to reduce the global temperature, we have the many way to reduce the temperature, including the carbon dioxide reduction. There are many ways to reduce the carbon dioxide reduction, including, the first, the popular method is to use the renewable resources such as solar power, hydropower, wind power, or biofuel. Moreover, Thailand can produce the crude palm oil about 2 million tons a year. To utilize the domestic material, we came up about to produce the biofuel from palm oil. There are many processes that can produce the biofuel from palm oil, but the one popular process is the pyrolysis process because it's cheap and simple and don't need any oxygen to proceed. But pyrolysis process can use with many types of catalysts, including the acid catalyst or base catalyst. But if we want to produce the biofuel from palm oil, base catalyst is better because it can reduce acidity in bio oil. Moreover, Thailand also produces the gypsum as a byproduct from mammal power plant about 1.5 million tons a year. So my objectives are the first one to study of biofuel production by catalytic pyrolysis of palm oil using calcium oxide, magnesium oxide catalyst derived from synthetic gypsum via packed bed reactor with different reaction temperature. And the second one is to study the effect of variant magnesium percentages. Let's move to the experimental part. The first one, we have to synthesize the calcium hydroxide first and use the gypsum as a raw material. The first step, we need to mix the gypsum with the sodium hydroxide and then wash it by water and dry it in the oven. After that, we got the calcium hydroxide. After we got the calcium hydroxide, we have to mix it with the magnesium carbonate and bentonite. For the amount of magnesium carbonate is according to the percent magnesium, according to magnesium percentage that we want to control. And each component or each composition of each catalyst was shown in this table. After that, after mixing the bentonite, magnesium carbonate, and calcium hydroxide by bond mill, we need to dry it, pellet, and calcite it at 750 degrees Celsius for 4 hours by furnace. And then catalyst and pyrolysis oil were characterized by all this equipment. The pyrolysis process pyrolysis reactor diagram was shown in this slide. The product from pyrolysis process we call final liquid product, and then we need to remove the water from the final liquid product because it came from the reaction that called deoxylation and hydrodeoxynation. After that, we have to remove the grease, and then we label it as the pyrolytic oil. After that, we have to distill it by distillation machine, and then we got a biogasoline, biokerosene, and biodiesel. Is produced from its distillation temperature. The next part is result and discussion. The first part we are focusing on the catalyst. The catalyst was characterized by XRD. It can prove that our catalyst has the calcium oxide and magnesium oxide. Moreover, the calcium hydroxide that we got at the first part can prove by XRD that we can make the calcium hydroxide from gypsum. Moreover, for Fe same result, it confirmed that our catalyst has the cold lactic fringes described by heterojunction. Moreover, the catalyst was from the Fe same. It showed that we can mix the catalyst with the good mixing. In terms of the composition in catalyst, it confirmed by XRF that we can produce the catalyst with the low sulfur, even the raw material has a high sulfur. Let's move to the pyrolytic oil. Our pyrolytic oil can be characterized by FTIR. It shows three important peaks. The first peak is represent to C double bond O, and the second peak is represent to CO bond. These two important peaks is related to the decarbonylation and decarboxylation. Moreover, the last peak is about 903 is represent to OH bond, described by phenol ester ether aromatic compound, which is similar to the GCMS result. Moreover, oxygen amount in bio oil it is lesser when we use the high magnesium percentage in catalyst, because the magnesium oxide can support the reaction, especially decarbonylation and decarboxylation. That's why the oxygen amount in pyrolytic oil is low when we use the magnesium amount in catalyst. For this two product, this two product is gasoline, kerosene, and diesel. But for light distillate, it represents to gasoline and kerosene. The maximum percent volume of light distillate was about 75% at 525 operation temperature with 10% magnesium. Because the excess of magnesium percentages can support the second cracking and produce more diesel with the less light distillate. And if we focus on the reaction temperature, it shows that the high reaction temperature can crack more hydrocarbon chain. That's why we got the high gasoline and high kerosene. For the property value, only the heating value and viscosity are in the standard, excepting the acidity is still high. So we can conclude that our pyrolytic oil of cooking oil taken place in packed bag reactor under atmosphere with no external gas using calcium oxide, magnesium oxide catalyst was successfully produced. And the second one is the calcium oxide synthetic was succeeded by gypsum at 750 degrees Celsius of calcination temperature. The third one is dilation temperature and magnesium amount in catalyst affect the product significantly. Then the last one is the maximum volume of glycerol was about 75% at 5 to 5 degrees Celsius of dilation temperature with 10% magnesium. Thank you.
Okay. This is very interesting, and thank you very much for your nice presentation. And now we have any question or comment? We still now the time is already up. Have any question? If no one, we will move.
So can I tell you about the slide? That is not the slide that I want to present, but it's the backup slide that I had right now. So it's not the sec. Yeah, I'm so sorry about the
it's okay.
Yeah.
Maybe I ask you is better. Can you tell us about did you try about the catalyst, the usability? Please turn on your
not yet, but that is my future plan. Yeah, for the second lab. Yes.
Okay. So now because the time is already up. Okay, but that's good. Okay, thank you very much for your presentation.
อาจารย์สุรชัย สวัสดีค่ะ
สวัสดีครับ Okay, so now the season 6 for all presentation is already finished, and thank you all presenter. And so now because the time is already 3 p.m. maybe we have to continue to the next season. อาจารย์ชนาทิพย์ please.
Yes, thank you, Dr. Surashai, for serve our share in the symposium. So according the time already delay from the schedule, so we will continue to the next session. So I would like to introduce Professor Prasad from Chulalongkorn University to organize next session. Please, Dr. Prasad.
Okay, thank you, Professor Chanatip. And anyone can hear me right, I think. Okay. For this, this one is the last session of today's for the International Symposium on Young Scholar and on Carbon Resources Conversion. And we would like to open this session with the invited speaker. And then we have 6 oral presentation, but anyways, one oral presentation cannot be joined today. Anyways, we would like to start with the invited speaker. With you can see in this slide that we have invited Professor Norinaka from Department of Chemical System Engineering from Nagoya University. And let me give a short introduction of his careers. He first got the PhD degree in chemical engineering from Hokkaido University in 1999. And he started his career as a research associate at Tohoku University. Then he moved to Germany at Karlsruhe University as Alexander van Hofbouw Fellows. And in 2002, and promoted as a senior scientist in 2004 at the same institute. After that, he returned to Hokkaido University as an associate professor in 2006 and moved to Kyushu University as the same position. And as present, he is a full professor at the Nagoya University. He started his career at Nagoya in 2017, and at this present, he served as director of the Institute of Material Innovation in Nagoya from 2018. And in past 5 years, he published a lot on the well-known journal, as you see in the slide here, in Energy Fuels, ACS, and Sustainable Engineering, IEC, and in the International Journal of Chemical Kinetics, with simulation, CO2 conversion, and also the fluid dynamics simulation. Okay, please welcome him, and today he will give topics of the presentation is a new concept for the low energy. A new concept for the low energy CO2 capture with LNG coal. Please welcome him.
Okay. Thank you very much. Can you hear me?
Yes, yes.
Okay, thank you very much for your very kind introduction, and I'm very happy to present and to share time, all of you here now, and I'm very happy to have the opportunity to see you again. So we met in the last, the first this symposium. It's a very nice symposium and very nice community, I think. So, and I'm very happy to share time and to share our recent activity on the CO2 issue. Okay, then can I share my slide? Okay. Okay, now you will. Okay, now you are looking at my slide, and okay, then go to the presentation. Okay, so let me start my presentation. So today I would like to talk about a new concept for the low energy CO2 capture with LNG called. So this is okay. So I'm Koyo Norinaga, Nagoya University. Okay, then. So this is, so all of you know, so let me introduce the where it's Nagoya located. Is just exactly the center of Japan. So between, we are in between Osaka and Tokyo. So, and so our university is very close to the place where the Toyota Motors are founded. So we have the auditorium in the campus, which was donated by the former president of the Toyota car company. So we call this as Toyota Auditorium. So Toyota is a company name, but actually the name of the person who founded the Toyota is a Toyota. So it is a little bit different. Okay, so this is our campus and where we located. So then, so let me introduce our laboratory. Is now we have very the big group, the more than 40 people, and so this we got the picture in front of our auditorium, Toyota auditorium, and now we have 16 academic and well-as supporting staff, and also 25 students, including the students from abroad. So in particular, we have a lot of the students from China, and also we have the students from India, and also now we accept from the students from Chulalongkorn, so from Thailand, and we also have now assistant professor from Thailand. So I will introduce what she's doing later. And so our research group is exactly focused on chemical engineering, and we are, in particular, we are doing about separation and reaction engineering. And we have one of the features of our research group is we have a lot of collaborations with industry. So the companies who make steel and who make energy, the gas company, and also who make some plant facilities. And also we are collaborating with Toyota also. Okay, so this is recent our studies of our research group. So published in the last year and this year. So this is one of the studies, so which we are doing the very complex chemical reactions included in conversion of the carbon resources such as the coal and also biomass and also waste plastic. And we are doing the modeling for the completion reactions occurred in the reformer of these carbon resource conversions. And also we couple with this complex reaction with the fluid dynamics, and we can solve what is happening inside the reactor. So we make some, we are invited to write a review of this computational fluid dynamics. So this is published and recently, and also we are, the next one is very related to what I will talk about today, is about the CO2 capturing issues, and we are proposing very nice new types of the solvent which can effectively capture CO2 and release the CO2. We can generate with a very small energy requirement. And we propose a kind of new process which facilitates the CO2 desorption by introducing hydrogen into the dissolver, and then we can facilitate the CO2 removal from the absorbent, so we can reduce the energy required for the CO2 capturing. So this is second one. And the last one is the to design the CO2 absorption liquid, and we predict phase behavior of this solvent by using quantum chemical calculations. This is also one of the fundamental studies, but it is very, we have the actually wider possibility to develop the new types of solvent. So this kind of method can help to facilitate to find the good solvent to capture CO2. Okay, then so today, so I would like to about the very future target, a very big hurdle. So now the Japanese government are organize a very kind of the project, which is we call the moonshot project. So this is very challenging. So, but we have to realize until 2050 to hold a net CO2 net zero emissions. So we have to make consider not only we capture the CO2 from the power plant, but also we have to think about to capture the CO2 even from the air. So direct air capture is one of the possible options to achieve the CO2 emissions to be zero, to mitigate the global warming. So this is so we join this project, and then what we are doing is we developed we are going to propose new types of the DAC system, which utilize the liquefied natural gas cold. So we capture CO2 and then we recover the CO2 other dry ice by utilizing the cold energy of the liquefied natural gas. So because Japan is a very big importer of the liquefied natural gas, we import 80 million tons of LNG per year. So but most of the energy of the cold energy of LNG is not well utilized, but wasted. So that's why. So we are looking at how to use this energy for the CO2 capturing. So this is the concept, and so this is so our proposed process is this is principally based on the chemical absorption process. So this process consists of the absorber where we collect the CO2 from the air selectively, and then so first so we can have the the air from here, and we capture the CO2 by the absorbent, and absorbent, which includes the CO2, to go to the dissolver, and then this dissolver, normally we apply the heat to evaporate the CO2 to release the CO2, but this case we use the cold energy of the air energy, and then CO2 gas is collected and converted into the solid. Then we can depressurize, decompress this dissolver without any mechanical pump. Just we cool the CO2 and to make the dry ice solid, then we can reduce the pressure inside the dissolver. So we can make the CO2 release, enhance the CO2 release by the decompression by utilizing the phenomena of the sublimation of the CO2 by using the LNG cold. So we call this process is the cryodeck, and we make this pressure swing amine process driven by the cryogenic pumping with the LNG cold. So this is advantage we think how this process is we can minimize the thermal energy input. So because we use not temperature swing, but we make this process by pressure swing. And also we can also by using this system with the water in air, also can be accepted by this amine process. So other process to use, for example, membrane or absorbent, solid absorbent is very don't like to welcome the water in the air. But our process can accept the water moisture in the air. And also we can recover the high pressure and high purity CO2 without any compression system, because we collect the CO2 as a dry ice, and then we, in a closed system, if we can heat the dry ice, then we can make the pressurized gas can be recovered. So it is very suitable for the subsequent CO2 utilization and storage system. So this is one of the advantage. And then if we compare our deck, cryodeck with other decks already developed in other countries, so the systems developed in other decks is always use their temperature swing method to capture the CO2 in air, but they need a lot of thermal energy input because they use temperature swing. But our system is to utilize, we utilize the LNG cold, and then we don't need any heat to dissolve the CO2 from the liquid, but we just depressurize the decompression of this dissolver by sublimating the CO2. So that's why, so we don't need any thermal energy at all. So we have the, so we have to, this is, yeah, the target value actually, but in the principle, we can achieve, we want to achieve this, minimize the thermal energy input. Okay, so that's all what we are going, I want to talk about these topics, but let me introduce about, so this community, so we are now accepting the assistant professor who got the master, the Stada Siddhison Bunchai. So she's also joining this symposium, and she it's got the she's her master of science from Professor Samat in Tamasato University, and also she got Professor Gan as a supervisor in the Hirosaki University, and now she joined our groups as an assistant professor, and she's now doing the very nice work on the CO2 electrochemical reduction. And she developed very nice new electrocatalyst metal nanowires, and then now we have very good result for the CO2 reduction, and we got very high selectivity to convert CO2 into CO. So Faraday efficiency is more than 80%. And so that's very interesting. So she's now looking at the conversion of CO2, electrochemical conversion of CO2. And also, yes, so now we accept the student from Professor Prasad Ankara Kempechi. So she is doing the CO2 methanation in our laboratory, and she's very hardworking. And we have the YouTube channel. She's also doing some video is also created in the you can look at the how the experiment works, and so we collect a lot of experimental data to develop the kinetic model for the CO2 methanation. Well, so both of the students and the staffs are also so we can see this community is very good to facilitate the collaboration between us, right? Okay, so I'm very happy to have the opportunity today, and I'm very eager to make the collaboration and also accept the also students, and also but this community is very good and very many potential young students and scholars are gathered here. So we are doing the CO2 utilization, the biomass conversion, and also CO2 capturing. So if you are interested in these topics, maybe you can join our groups and do the very interesting research. Okay, so thank you for your kind attention. So so thank you so very much. So we are looking for the future collaboration. Thank you very much.
Thank you for your nice presentation and the recent work on the CO2, maybe the utilization, I mean the both absorption and utilization. Good. And also Nagoya is also welcome all of the students and also the collaboration in our country, China, Thailand, Japan, and the others. Okay. If anyone have a question, please write in the chat box or open the mic and ask the Professor Nunirabai directly. And at this moment, for the waiting for the question, I have just a short question on the CO2 and LNG. Could you give me some estimation that how many LNG equal to CO2? I mean, how many for 1 ton of LNG? How many CO2 that you can produce at this time by the estimation?
That's fine. So very important issue. So we have this principle of this method is to convert the latent heat of LNG. So LNG is a liquid and then vaporized. So when vaporized, LNG vaporizes, they need the heat. They need to absorb the heat. So this heat, we need to exchange the heat for the sublimation. So which is convert CO2 gas into the CO2 solid. So they release the heat. So this heat is absorbed by the LNG vaporization. So if this heat exchange is the principle, so then we can estimate how much CO2 can be sublimated by the LNG cold. It's so rough estimate. So we can sublimate around 0.8 ton CO2 if we use 1 ton LNG. So that's is the potential of this method. So if we utilize the vaporization heat for the CO2 sublimation. that convert CO2 gas into the CO2 solid, dry ice. Yes, so that is the maximum potential by utilizing this method. Yes.
Okay.
Yeah. So, but we have to look at the the mechanism and also develop the systems to achieve such a potential amount of the CO2 absorption, CO2 recovery. Yes.
It's really good because I'm not sure that the situation or the current process in Japan, but in Thailand, we still have no idea how to utilize the coal of the LNG. In some areas, they just use the coal to make the heat absorption for the solar panel, and some just use the coal energy for the growing some flowers that is require the coal areas temperature only.
Yes,
it's really
so,
new for us.
Yes, so it is very interesting. So if this system is good for the CO2 reduction, maybe so we can collaborate. So all of the LNG importing countries. Yes.
Okay. It's almost the time, and thank you again, Professor Nolina, and hope that we can see each other very soon. Maybe next year, I think.
We can see very soon. Yes, I'm looking forward to see you again, all of you also. Yes.
Okay. Okay. Thank you very much. Okay. For the next is we're going to the oral presentation, and the first one I would like to ask the speaker, Yulin Yan from the University of Science and Technology, Liaoning. He will give a talk on the topic of major technology and their application for oil shale. Okay, I hear you. You can start right now.
Can you hear me?
Yeah, sure.
Can you hear me?
Yes.
Yeah. Good afternoon, everyone. My name is Yan Yulin. I'm from College of Chemical Engineering, the University of Science and Technology Liaoning. Today, the topic is mature technologies and their application for oil shale resulting in the world. Summary. Definition. Oil shale is an sedimentary rock containing organic matter, which is a low calorific value solid phase filled with light gray to dark brown color. World oil shale resources. Oil shale resources are abundant in the world, and its mineral resources are everywhere, but their distribution is not balanced. The total proven oil shale reserves in the world are about 500 billion tons of shale oil, 2.5 times the proven oil reserves in the world. Oil shale technology and underground retorting technology. Underground retorting is carried out by heating of the oil shale in situ without requiring excavation and processing of the oil shale at the surface. Common underground retorting technique. In Peru, underground retorting technology, electric freezing and electric heating retorting technology. The advantage of the underground retorting technology is that it avoids mining of the shale and the exploitation cost is low. The disadvantage is that shale oil yield is low because shale oil and retorting water is key, and the leakage pollutes groundwater. Oil shale retorting technology, above ground retorting technology. For the above ground retorting, oil shale must be mined, crushed, screened, and transport by the belt in the retort for distillation. During crossing, oil cell is sieving into large and small particles to suit different retort types. At present, the massive cell retorting technology has been widely used and matured in the world. China Fusun type retort, Brazil Para 6, small particle retorting technology, Estonia Garrett, Canada ATP, China Fusun type retort. By the way, before I studied as a doctor, I worked in the cell oil plant of Fusun Media Group. This is the picture of the factory where I worked. Fusun processor technology. The cell processing capacity is 100 tons per day, with a unit of 20 retorts, sharing a heating chamber and a condensing recovery system. Oil cell with a grain size of 10 to 75 millimeters is processed. The upper section of the retort is drawing and paralyzing, and the low section is gasification and combustion of the cell semi-coke and air and steam isomers products, cell oil, residue pyrolysis gas. Fusun oil cell is a byproduct of the coal mining, so the feedstock cost is very low, and there can be larger profit margin. Brazil Para 6. Para 6 is a vertical cylindrical retort. Two sides of the retorts have been successfully operated. The diameters of the retorts are 5.5 meter and 11 meter, and their capacities are 1,600 and 6,000 tons per day, respectively. The grain size of the oil cell is 8 to 50 millimeters. The upper stage dries and pyrolyzes the oil cell. The low section cools the cell trunk and recover heating using circulating pyrolysis gas. The heat required enters from the middle of the retort. The gas is heated by a turbulent furnace. Products: cell oil, high calorific value retort gas. Estonia Garrett. Estonia Garrett. Garrett's retort is a horizontal cylindrical retort can using a sluice as heat carrier. At present, through variation of the Garrett process operates in Estonia. Oil cell particle size 0 to 25 millimeters. In the retort, the per-drawed cell is mixed with the hot cell ice and heated to 500 degrees, after which the cell oil and the pyrolysis gas are extracted. Cell trunk and the cell ice enter the vertical fluidized band combustion chamber, and the high temperature cell ice generated is then recycled to heat oil cell. High temperature flue gas is used to preheat oil cell. The processing capacity are 6,000 tons per day and 3,000 tons per day. A retort yield of the oil cell in aluminum retort is 85 to 90%. High calorific value retorting gas is produced. ATP. Look at this picture. This larger equipment called ATP is also in my factory. ATP was developed by a Canadian engineer, William Tasuk, and two plants have been built, one in Australia and another in China. The daily processing capacity of the oil cell is 6,000 tons. Cell grain size is 0 to 25 millimeter. The oil yield is 85 to 90%. Tasuk processor diameter 8 meter, length 60 meter, horizontal cylindrical retort can, solid heat carrier retorting technology for processing juice in one machine, oil cell drawing, oil cell pyrolysis, semi-cook combustion, heat recovering from spent cell and combustion gas. Products, cell oil, gas with high calorific value, cell ice. Cell oil is fractionated into naphtha and fuel oil, and naphtha is hydro-refined into a low sulfur product. Comparison of various processes. In situ technology was developed over the past decades, led by cell. Ex-situ technology can be roughly divided into larger particle lump oil cell and small particle oil cell processing. Fusion lump cell process is suitable for the processing of the oil cell with low oil content, and it is suitable for small and medium-sized factories with low investment. Basil, the Paragraph 6 lump cell process is suitable for oil cell with high oil content and high calorific value of retort gas, which is suitable for large-scale factories with high investment. Estonia guard process for fan oil produced high calorific value gas at high feed rates. The process is complex with high cost of the cooperation and high capacity suitable for mass products. Australia and China are suitable for fan oil cell with high or low oil content and produce the high calorific value gas at a high feed rate. It is suitable for large scale factory with high investment. Thank you for your attention. Thanks.
Yeah, thank you very much for your nice presentation, and the result of the shell oil is really interesting. Does anyone have some question? For the time, I think only one question is for this time. Okay, hello.
Hello.
I just have only one question. How about the cost of the oil?
The cell oil is 3,000 yuan. 3,000 yuan. 2, 3.
Okay.
3,000 yuan. Okay.
3,000 yuan. Okay. Thank you very much. It's very interesting that you have a really big size of the reactor and also the big size of the scale. Okay. Thank you very much for your presentation. Okay, next I would like to introduce our speaker, Mr. I guess Hong. So sorry, Miss Hong Chang from Shenyang University of Chemical Technology. She will give a present in the topics of. Sorry, I lost it. The topic of. Yes. Just wait for your slide. Okay, then you can start right now.
Okay. Good afternoon, everyone. My name is Zhang Hong. I come from Shenyang University of Chemical Technology. The topic I report is the characteristics and kinetics of thermal decomposition of solvent in microfluidized bed reaction analyzer. I will report from the following 4 aspects: The first part is background and significance, improving utilization efficiency of refractory iron ore resource is a common theme for the development of the world's steel and iron industry. As is shown in the pictures, China's iron ore reserves rank among the top 5 in the world. Siderite is a common iron ore. Its main component is ferrous carbonate. It has abundant reserves, but due to low iron content, its utilization is low. Therefore, it is very important to improve the utilization rate of siderite resource. Now, magnetite roasting followed by magnetic separation is the most commonly used process. The process converts siderite to magnetite, showing high magnetic susceptibility and high grit. But the thermal decomposition of siderite is quite complex, and the final product depends on the roasting atmosphere. Such as in inert atmosphere, the total reaction can be divided into 2 single reactions. The first follows the equations. Currently, the thermal decomposition kinetics of siderite are mainly measured using TGA and self-made roasting experiments.
Hi, hello. I cannot. It's the sound is not good. Anyways, please go on and.
Okay. In the suspension process to lead to the non-uniform distributions of temperature and reactant concentration in axial and radial directions. Meanwhile, both of them have not studied the 2 single-step reaction kinetics and the characteristics of gas generation. The microfluidized bed reaction analyzer is a new method and new apparatus for gas-solid reaction analysis. The schematic diagram is as follows. It mainly includes 5 parts. The microfluidized bed is only a few tens of millimeters in diameter. It can realize instantaneous passing of materials and online gas product analysis. At the same time, it has unique performance such as isothermal differential characteristic, high rate of mass and heat transfer, and uniform temperature distribution and good mixing diffusion. Therefore, the purpose of this study is by using MFBRA to show the characteristics of gas product and the kinetics of single-step reaction. Siderite raw materials obtained from China's Hunan province. The particle size is 120 to 250 microns. The following results are measured by XRF and XRD. The third part is results and discussion. The following picture shows carbon monoxide and carbon dioxide formation curves. It can be seen that the increase of reaction temperature is decomposition of siderite. When temperature increases from 4 to 700 degrees Celsius, the time for complete decomposition decreases from 350 seconds to 6 seconds. Moreover, we can see that the time of carbon monoxide generation is later than that of carbon dioxide release. And as the temperature increases, the time interval decreases from 1.1 to 0.1. This result indicates the decomposition reaction of siderite and there follows 2 steps. Here further explain the appearance of the experimental results. The picture shows mass response to a direct pulse input into microfluidized bed by the gas mixture containing carbon monoxide and carbon dioxide. we can obtain both gas products have the same response speed. The next is the content variation of carbon monoxide and carbon dioxide, and the different temperatures obtained from Mars and JC are shown in picture. Both result data obtained are almost the same. The trend of both carbon dioxide and carbon monoxide content with an inflection point at 550 degrees Celsius, which may be related to the effect of thermodynamics. The next picture shows the relationships between conversion and reaction time for decomposition of siderite at different temperatures. It seems that the higher the reaction temperature, the shorter the time required for complete decomposition. Magnetization reaction pictures. As the reaction temperature increases, the conversions corresponding to the maximum reaction rates gradually increase. The fourth part is the isothermokinetic parameters in MFBRA. By fitting the data obtained, the activation energy of ionization reaction and the magnetization reaction are as shown in the picture. The table shows 5 models that are commonly used for the siderite magnetic roasting reaction in the literatures. By model fitting, we obtained the first step decomposition reaction with the geometrical contraction model, the second step of magnetization reaction with the 3-dimensional diffusion model. The last part is concurrence, many include the following 4 contents. Firstly, the gas product carbon dioxide is generated earlier than the gas product carbon monoxide. Data indicates the overall process of siderite decomposition can be divided into 2 single steps. By fitting the data obtained, we further deduce the 2 single steps isothermokinetic parameters in MFBRA. Secondly, the variation trend of the contents of both carbon monoxide and carbon dioxide generated with temperature is opposite, with an inflection point of 550 degrees Celsius. Lastly, the increase of reaction temperature accelerates decomposition of siderite. As temperature increases, the time for complete decomposition decreases. That's all my report. Thanks for your attention.
Okay, thank you very much for your nice presentation. Are there any questions from the audience? You can leave the message in the chat box. Also, you can open your mics if you have a question. Anyway, while waiting for the question, I have one question, but not the technical question. I would like to know that for the microfluidic bed reactor analyzers, how the size of the reactors? I mean, how big of the equipment? And how yes, how many? And how about the test exam, for the exam, if you would like to do a one-time reaction, how many grams? Okay, very few, 10 to 20, 10 to 30 milligram.
The microfluidized bed is 20 millimeter in diameter.
A very small one is a really useful equipment. Okay, that is all my question, and I think it's time, and I would like to thanks to you for your nice presentation.
Okay,
thank you. Yes, thank you. Bye bye. And for the next speaker, I would like to ask the Piyanat from Khon Kaen University. Okay.
Can you hear me?
Okay. Yes. Okay. She will give a talk in the conversion of paper sludge to coal-like via hydrothermal carbonization in the effect of process condition on physical and chemical properties. Okay, if you are ready, please start right now.
Okay, thank you. Hello, everybody. My name is Pinut Putong Khao from Khon Kaen University. Today, I would like to present conversion of paper salad to chloride via hydrothermal carbonization effect of process condition on physical and chemical properties. I'm here to talk to you about the introduction, experimental result, and discussion, and the last is the conclusion. I'm going to start with an introduction. Nowadays, the global is a facing shortage of fuel to produce energy, such as the coal reserves are enough for another 150 years. Natural gas for 400 years. So new source of energy must be searched. In addition to renewable fuel, the hydrothermal technique for processing advanced functional material is becoming the most popular among scientists and technologists in a variety of applications. And the term of material preparation under the action of pressure and temperature in a closed system. The hydrothermal carbonization is a type of induced qualification process that it can convert biomass or waste into a chloride product shown in a high carbon content and high heating value. The hydrothermal carbonization, or we can say HTC, can change the raw biomass or waste to the chloride by many reactions. You can see reaction in this slide. In this process, we have to control in an aqueous solution and without the oxygen gas. Many research has been used many precursors for HTC, such as natural biomass, natural polymer, municipal waste, and industrial waste. We are interested in use industrial waste as a feedstock and issue paper salad waste in this work because it has a low ash and high heating value. The paper salad is mainly used for filling or cell cover. If it can be converted to chloride, it will increase the value. So in this work, we find the suitable condition of the chloride synthesis from paper salad on physical and chemical property in the three factors: temperature, time, and liquid solid ratio. The scope of this work you can see in this slide. And the experimental according to the land condition defined by the Bock-Bengen design in the effect of temperature, time, liquid solid ratio, and experiment were performed according to 15 conditions shown in the right hand. In this slide, show the step of chloride synthesis start from the raw paper salad die overnight, and after that mix with the ice water following a liquid solid ratio from the design condition, and we purge the nitrogen gas to remove all of oxygen inside the reactor, and then we operate the temperature and time following the design condition. When finished, we separate the liquid and solid by using centrifugal technique and take a solid to dye the solid product we call to the chloride. We obtain the product and analyze by many techniques. You can see the technique in this slide. For the liquid product, we use a TOC to confirm the leaching from the solids, and we use a chloride yield, energy densification, and energy recovery as a response from this work. You can see our equation shown in this. And for the ultimate analysis, we use the Van Cortlandt diagram to confirm the chloride for the solid OL. Result and discussion, you can see that in this slide, we have many reactions occur in our process, start from the hydrolysis and the end of our aromatization. From this, we will show in our results. For the hydrolysis, you can see that we start from the raw paper salad base, and we compare when we increase the temperature reaction. You can see that the fixed carbon and high heating value increase on the same of reaction time and liquid solid ratio. And when we increase the reaction time to 6, you can see the result show the same of increase the reaction temperature. That means positive effect on the fixed carbon and high heating value at the high temperature. But at the low temperature, the fixed carbon and high heating value had a similar value. However, the yield of the product should decrease when increase of both effects. And when in this slide, when we increase the liquid solid ratio from 12 to 20 at the low temperature, the fixed carbon high heating value and yield did not change, but at the high temperature, when increase the liquid solid ratio, the fixed carbon and yield were slightly increased. However, when we increase the temperature in conjunction with increase the liquid solid ratio, the results showed that the fixed carbon and yield increase, but high heating value decreased. Therefore, the temperature and liquid solid ratio have an interaction. So for the optimization reaction on this side of experiment, we use a normal probability to look at the error of our results. You can see the twice you almost of one. That meaning you cannot get found the error from all of the run order, and you can see all of response from the calculation and experimental from the figure of the time series part. The results show the almost of the same, and R square have over 90%. And for the calculation, we use the quadratic equation shown in this slide. And when you look at the main and interaction effect, you can see that for the yield and energy recovery, all of effects show in negative effect on response. The mean is that when we increase our temperature or time, the yield and energy recovery will decrease. However, you can see the interaction effect at the temperature and liquid solid ratio show in the positive effect, which is consistent with the experimental results. After we check accuracy and precision by using ANOVA, you can see that the lack of fish show the insignificant effect on regression model. The mean is that our experiment show the accuracy and precision. And when we analyze the total organic carbon in liquid product, you can see when we increase the reaction temperature, the total organic carbon increase. However, if we fix the reaction temperature but increase the reaction time at the highest reaction temperature, you can see the total decrease. That means the aromatization reaction occur at the high reaction temperature and take a long time. And if we use a temperature lower than 220 degrees Celsius, we can see when we increase ratio of liquid and solid, the total organic carbon is increased. From this result, we can say that hydrolysis reaction occur in our process. And for the FTIR spectrum confirm decarboxylation and aromatization reaction. For the decarboxylation reaction, you can see wave number 1060 show the CO staging appear when we take the temperature at 200 to 220 in our product compared with the raw paper slash waste. And at the wave number 700 to 800, you can see at the high temperature, we can absorb an aromatic bonding. That means the aromatization reaction occur in our product. That's why the total organic carbon from the liquid show decrease. And when we look at the morphology, you can see that the raw paper salad look like a fiber and not roundness. When we take in HCC at the high temperature and the long time, you can see the morphology change to a spherical and accumulate is cut to shorter than raw paper slab. For the CHNO, you can see that we can change the paper slab base to the lignite length. For the condition for chloride production was achieved, we get at a 220 degrees Celsius 6 hours and 16 of liquid solid ratio. We can get the yield, energy dissipation, energy recovery, high heating value. All value shown in this table. However, in our product, when we compare the high heating value with the outer material, you can see the chloride show the almost 25 megajoule per kilogram. In this show higher than outer material. That's one we can say the chloride is the high heating material, and when we compare with the outer product situation in the lignite range. For the conclusion, paper salad waste use a substitute biomass for produce chloride by hydrothermal carbonization process, and temperature and time are significant parameters for yield, energy densification, and energy recovery. The condition of chloride production were achieved at 220 degrees Celsius 6 hours at liquid and solid ratio of 16. It can produce renewable fuel called chloride in a length of lignite coal based on one current diagram. I would like to thank all for support in this verse. Thank you very much.
Okay, thank you very much for your nice presentation and the new way to use the carbon sludge. Are there any questions from the participant? Anyways, while waiting the question, I have just only one question: that how about the density of the carbon light? I mean the US products. Is this close to coal or the different?
Density.
Have you tested this? Yes, density.
Now
still on the progress.
No, I don't test. I just.
Anyways, beside the density, how about the physical appearance? Is this a lightweight or the?
It's a lightweight.
Okay. And so I hope to see more results in the future.
Okay, thank you very much.
Yes, thank you for your presentation.
Thank you.
Okay, I have one question.
Okay, yes, good. Sure.
In terms of total solids, what's the yield of the hydrochar?
Yield.
Yes, the total yield of your products.
Oh.
In terms of total solids.
Okay, total yield. Oh, sorry. Okay. The yield are 40%.
Okay, 40%. Okay, that's a 40% to the total feedstock, the paper sludge, or the total solids of the initial solids.
Okay.
40% is based on what? 40% of what? What is the total paper sludge you put into a system, or the total solids, initial solids?
Just only the paper salad, right?
Yeah, paper salad.
Okay, you mean when you use the paper salad 100 gram, you can get your product 40 gram?
Yes.
Oh, okay.
Because you miss, you get you put 100 kilogram of, say for example, you put 100 kilogram of paper sludge, and you get a 40 kilogram of the hydrochar. Okay, good.
Okay. Yes.
Very nice job.
Okay, thank you very much.
Okay, thank you for a nice presentation. Okay, I would like to move to the next presenter. Our next speaker is I'm sorry, just a moment, please. Okay. Miss Xiu from Taiyuan University of Technology, and she will give the talk in the simulation of copolarisis process in laser via structure-based mass transfer model combined with the discrete DAEM Please introduce. Okay, I can see you.
Can you hear
Yes.
me?
Okay. Yes. Good.
Okay. Thank you, sir. Hello, everyone. My name is Pan Xuer. I'm from Taiyuan University of Technology in China, Taiyuan. I'm very glad to be here for introducing my research content. My topic is simulation of co-pyrolysis process in rather well structure-based mass transfer model combined with the discrete DAM. First, by comparing the world and China's primary energy structure in 2018, we can see that the proportion of coal is still higher than 50% in China. And further, according to our country's coal consumption from 2008 to 2018, we know that the coal-based energy structure is not early changed in the short term. And the low-rank coal accounts for a relatively larger proportion, and its volatile and water content are higher, which is not conducive to the direct combustion and gasification. Pyrolysis, which can first convert its volatiles to extract high-value coal tar and gas, and then the left tar and can be used for combustion and gasification, is a more efficient way to utilization of low-rank coal. As for the coal pyrolysis kinetic model, empirical models are widely used, and they are mainly divided to 5 kinds. Overall first-order reaction model considers coal pyrolysis consists of 1 reaction, while the dual parallel competition reactions model is 2 reactions, and then finite multi-parallel reactions model is suggested finite reactions. But as for the functional group model, it based on the finite multi-parallel reactions model further considered that each product is generated by the corresponding specific functional groups, which is getting more close to the actual reaction's physical meaning. And at last, the distributed activation energy model, DAM, is considered that the coal pyrolysis to unnumbered. These 5 models is getting more closer to the actual coal pyrolysis reaction and begins to have the physical meaning. Herein, the DAM model is relatively simple but more accurately and the most widely used here. But when it combined with the CFD, its integral greatly has the impact on the calculation efficiency, considering that the general Arrhenius formula can be easily coupled with CFD. Then we chose to discrete the DAM. And in this way, the 3 exponential factors and weights for each reaction could be considered separately. Then it can be combined with the CFD in a desired calculation efficiency, and the simulation results are even more approached to the experimental data. Here, the Rather reactor has been widely used in chemical engineering industrial, especially in the fluid catalytic cracking reaction. Owing to its advantages of larger processing capacity, high heat and mass transfer efficiency, and the continuous operation. Here, the FCC process is an ultra-fast reaction, and its intermediates are the desired products, which is similar to the coal pyrolysis reaction. And because of the strong heterogeneous solid flow structure, the mass transfer coefficient showed number in the rather shows a significant dispersion, and in the range of 3 magnitude at least. And thus, we maybe cannot accurately describe the corresponding mass transfer in reaction process. Then the heterogeneous mass transfer model is proposed, which divides the structure into dilute and dense phase. In these two phases, mass transfer between gas and solid is carried out through convection, diffusion, and reaction. Then the obtained mass transfer, Kf, can be more truly reflected the values from experimental data when compared with the homogeneous mass transfer coefficient. And now we have got the mass transfer coefficient Kf, and how does mass transfer affect the actual reaction? Here we have the comparison between the whether or not exists the mass transfer. First, if we have no mass transfer, the reaction is just from particle to gas, and the only reaction is needed. But if the mass transfer is involved, the reactant is first from the particle main body to its surface and then move to the gas. And the balance equation of mass transfer and reaction is built here, considering the effect of mass transfer. And there are the simulation equations detailed. And in the three parts, the influence of diameters are considered. Here, the influence of particle diameter, when it increased, it has a not obvious decrease in Chi-S, Chi-F, and Chi-SF, which may be a result from the prolonged reaction route from the particle to its surface. And then the reaction rate is also, the reaction temperature is also investigated here. With the higher temperature, the reaction is completed quickly, and the maximum yield of products is not changed with the temperature. At last, the distribution of mass transfer Kf is discussed here. From the left picture, the change of particle diameter makes the mass transfer coefficient Kf fluctuate violently. And it observed that when diameter increased, the Kf becomes larger. And the right picture shows that the temperature has no effect on the mass transfer coefficient, which it can be inferred that the Kf is not influenced by the reaction, which proved by Ho. Here, the main conclusions in this research are listed below. Like considering the non-uniform gas-solid flow structure, we can more accurately describe the corresponding reaction processes. And the change of particle diameter makes the mass transfer fluctuate violently. It observed that when diameter increases, the Kf becomes larger. And there are the main conclusions in this research, and others is not repeated here for brevity. That's all. Thank you for your attention.
Okay, thank you for your presentation. It's really nice one, really smooth. Okay, are there any questions from the audience?
Yeah, I got one.
Okay, please.
When you do the modeling, what's the fluidization state maintained in the riser? Is a bubbling fluidized bed or fast fluidized bed?
Fast fluidized bed.
Fast fluidized bed.
Yes.
Okay. It kind of strange for me why the mass transfer coefficient decreases or increases with a particle size.
Yeah.
Why? Well, can you give some explanation why the particle size increases, mass transfer coefficient increases?
We
Yeah,
firstly,
that's this slide here. The next one.
the next one. Okay.
The next one, the KF.
This one.
Yeah. You see the KF is larger for the large particles. And
Yeah.
it's almost zero for the smaller particles, small.
Yes. We think when the diameter is increased, the terminal velocity is increased too. Although the specific particles is decreased, but in these two influence competition and compensation and have increased influence.
Okay.
Okay, thank you, Professor Bayer. One question from the chat box. They asked that what software do you use in your simulation?
Fluent. Answer is Fluent.
Okay, thank you very much.
Thank you very much.
Okay, thank you for your question and answers.
Okay, thank you.
Okay, I would like to move to the last speaker of this session. Okay. From the, are you ready? I mean the city date.
Yes.
Okay. He will give a talk for our last presentations. Candidate from Khon University. He will give a talk on the conversion of sewage sludge from industrial water waste treatment to solid fuels to hydrothermal carbonization process. If you are ready, you can start right now.
Okay, thank you. Okay, everyone can you see my slide?
Yes, please press slideshow.
Okay. Okay. Good afternoon, everyone. I am Siridet Pabunmukan from the Khon University. I would like to present my research called Conversion of Sewage Sludge from Industrial Wastewater Treatment to Solid Fuel through Hydrothermal Carbonization Process. There are many topics in my presentation, which are sludge management, hydrothermal reaction, objectives, methodology, results, and conclusion. I would like to explain how harmful sewage sludge is. It causes a loss of pathogens, heavy metal, hazardous waste, and emission of greenhouse gases. We must use the proper disposal by sludge management as following: anaerobic digestion, landfill incineration, composting, pyrolysis. All sludge management that you have just listened have many pros and cons. Hence, I choose the hydrothermal process because it uses without dehydration, spends short processing time, and it is not major. So I will explain the type of the hydrothermal process. The first type is hydrothermal carbonization. The second is hydrothermal liquefaction. The last one is hydrothermal gasification. Then I would like to know the reaction occur in the HTC. I choose the HTC because I am interested in the solid fuel as product. So there, from starting cellulose would be hydrolyzed to HMF. Then HMF would be polymerized or aromatized to aromatic unit. And lastly, the aromatic units would be condensed to aromatic carbon network. Then after we know the reaction in HTC, the The factors affected on HTC is following from this slide, which are the temperature, pressure, time, solid liquid ratio, and types of biomass. Okay, so my objective has been separated to main objective and sub-objective. Main objective is to convert sewage sludge from industrial wastewater to solid fuel by hydrothermal compression. Sub-objectives are to study parameter effective on hydrochar properties and to study the effect of hydrochar blending with coal. Accordingly, I designed the schematics research. The okay. The conditions, which are the temperature, time, and solid liquid ratio. After HTC, I got the hydrochar, and then it would be analyzed by the solid catalyzed analysis following the left box. In case of processed liquids, it would be analyzed by TOC and ICP. After that, hydrochar would be blended with coal by the condition in your right hand. And then the last step, we use the hydrochar blended with coal for calculating kinetic combustion. It is the picture of my experiment. The first sewage sludge is naturally dry and completely mixed with the ice water before putting hydrothermal autoclave. And then I press the nitrogen for repelling contaminant for 15 minutes. After reaction, I put the product into the oven at 105 degrees Celsius for 1 day. And then it would be ground to the powder for continued analysis. From the results, as you can see, when the solid liquid ratio is increased, moisture contents volatile matter as massive would be decreased, but ash contents would be increased because of inorganic matter accumulating in solid fuel and organic matter dissolving into the processed liquids. That confirms by the result of TOC. Existing sewage sludge on HTC SS1/1, it has the highest heating value and the most carbon content. So I use the Venn diagram for classifying the types of solid fuel. After HTC, H2C and O2C of sewage sludge is reduced from biomass stage to lignite stage by dehydration and decarboxylation reaction. In case of metals, metal is solid product is no different level, but metal in processed liquids are fluctuated. In case of calcium and ferric in processed liquid, when the solid per liquid ratio is increased, they are obviously reduced. The metal detected for disposal evaluating in soil and water. So subsequently, TGA and DTG used for classifying the VM stage and charge state and calculating the kinetic combustion. After I calculate the kinetic combustion at HTC SS1/T, it is the highest activation energy of volatile matter. However, solid per liquid ratio is increased. The activation energy of char is no different. as is solid per liquid ratio. So even though the hydrochar has heating value, but it's not enough for direct combustion. So kinetic co-combustion would be investigated. As you can see, at the 30% HTCSS, it is the lowest activation energy of char. Although how much hydrochar added, the activation energy of volatile matter is hardly increased. Okay, I want to know about the S index that showed how much violent the burning of solid fuel. As you can see on S index of hydrochar, HTC 221 per 1 has the highest S index and the lowest ignition temperature. And in case of S index of hydrochar blended with coal, 10% HTC 221 per 5 has the highest S index. In the conclusion, 1:1 solid per liquid ratio condition is used to solid seawater sludge. It improved the heating value from about 12 megajoule per kilogram to 14 megajoule per kilogram, and carbon content from about 30% to 33%. Co-blended with hydrochar can reduce the activation energy at 30% hydrochar added. Thank you for your attention.
Thank you for your nice presentation. It's time for question and answer. Anyone have a question?
Yeah, this is Dion again.
Yes, thank you.
I got two questions for you. And first one, probably about the slide number 12 or 13 over there.
13.
Okay, the metal distribution in the liquid phase and the char. Heavy metals.
Heavy metal.
Yeah, and you should the metals separated in the processed liquid and the solid product. And the information I want to know is what's the partition? See the percentage of total metals ended up in liquid. See if you get 100% of metal after the hydrothermal treatment, and what's the percentage of metal goes into the solid liquid and what remains in the solid?
You mean
so what's the percentage of metals? Yeah, in other words, what's the percentage of metals removed by the hydrothermal treatment?
You mean from the raw material, right?
Yeah. So, see, for example, for the cadmium, what percentage goes to the liquid? What's the percentage left in the biochar?
So the question is, you have a metal, right? Yes. Some of the metal is in the solid. So we would like to know that, how about in the liquid? Do you have a metal or not? And what the percent if you have the data?
I analyze from ICP and it represent in the milligram per liter unit.
Yeah, you know the concentration for each phase, but you do not have the total mass balance, right? Have you ever done the mass balance?
Do you have a mass balance of all the component, a mass balance?
No, I did not do yet.
Okay. Okay. So if you do not, I really suggest you to conduct a mass balance to see what's the percentage. This is a good way. It's a good way to see how effective, the hydrothermal treatment is going to remove the heavy metals from the biochar, okay? And the second one is about the activation energy. Probably you go forward to the next one.
This?
Okay, yeah, this one. See, for the HTCSS 1 to 3 ratio and the third column over there.
Yeah.
And why this volatile matter has the highest active energy than the char?
I think it has the volatile matter in the product. It's not dissolving in the process liquid.
See, normally the char is hard to burn, right?
Yes.
Then the volatiles, and it looks like it's just opposite your activation energy number is suggesting. Any explanation to that?
I think
Okay. Yeah. If you never saw about it, just sort of think of that again. Okay. Thank you very much.
Okay, thank you.
Sorry, sir.
Thank you, Professor Bai. I think it's to the good question that maybe Citizen can go back and do some more research and more discussion on the result. Okay, thank you, Citizen.
Thank you for suggestion.
Okay. Thank you very much. Okay, here's the end of the session. I would like to get the microphone back to Professor Suwadi for the last of the event today.
Okay, thank you very much, Professor for staying up until the end of the conference. And I would like to thank all of the chairman and co-chairman for the conference as well. And I think this session will be very interesting for the student. Also, there is an announcement for the Best Presentation Awards that is hosted by Horiba Scientific. And also one more from Bioenergy and Catalysis Research Unit of Thammasat University. So I think now everybody ready for the Best Oral Presentation Award. Okay, the first one is, the first one. Okay, can you show your slide, please? Okay, the first one is Miss Nishaboon Chaihat from Hirosaki University of Japan. And could you show your screen, please? I mean your camera. And she presents about the Institute catalytic upgrading of bio-oil derived from pyrolysis of biomass over hollow HSF5 steelized. Yes, we would like to congratulations to you. Okay, so maybe the organizer will take a photo together first with your certificate as well. Okay, everybody. Okay, smile. Okay, is it done, organizer?
Thank you so much.
Okay, thank you very much for joining us. Okay, and nice work for your presentation. Okay, and next one will be Mr. Lee Kim Hong Pham from Thammasat University. Could you please show your camera, please? Okay. And Mr. Lee Kim Hong Pham, he presents about a preparation series of nickel phosphide, nitrogen doping activated carbon catalyst, and he shares us about the effect of nitrogen doping of hydrodeoxygenation of palm oil kernel shell. Okay, congratulations, Pham. Could you show your camera, please? I cannot see you at the moment.
Can you see my camera?
No.
Okay. I just a moment.
Okay.
Okay.
Thank
you very much.
Where are you? I didn't see you.
Can you see me?
No. Okay. So you are okay. You're next to me now. Okay. Congratulations, Farm. Congrats you again, and nice job for the presentation. Okay. And next one is Mr. Siu Roy Hong. Okay. Can you on your camera? Where are you? Okay, you're there.
Yeah, I'm here.
Yes. So the organizer will take the photo together, and Siu Roy Hong present about the evaluation of metallic magnesium production from low rank manganese. Okay, congratulations again for your nice presentation. Okay, the organizer, you take the camera. Is it done?
Okay, thank you.
Count on 3. 1, 2, 3. Okay. And next one. Nice job. Okay. Next one is Miss Ping An from Shenyang University of Chemical Technology. And she shares us about the optimization of energy efficiency for the flash calcination of magnesite in a transport bed. Okay, Ping An, where are you? Okay. The organizer, could you please move Ping An close to me? And then we can take a photo together. Okay. So okay, you're there. Nice to see you again. Last time we see you there as Yang, right? Last time that we met. Yeah, nice to see you again, and nice job for today. Congratulations.
Thank you.
Okay, so please stand by. We will take a photo together again. Okay. And the next one is Miss Wasipim Chansiriwat from Khon Kaen University.
Thank you.
Okay, are you there? Congratulations again. And Miss Wasipim present about the oxygenation of palm oil to light biofuel over the calcium-based catalyst derived from the gypsum waste under the atmospheric pressure. Okay, nice job for today. Congratulations. Okay, there is the award that sponsored by Horiba Scientific, and the last one, there is one more best oral presentation award that is sponsored by Bioenergy and Catalysis Research Unit. That is Miss Pan Suea from Taiyuan University of Technology. Okay, are you there?
Yes, I'm here. Thank you very much.
Yes.
Okay, thank you.
Nice job for today. The organizer, would you please keep the camera off pan close to me? And we will take a photo together.
Oh, yes.
Okay.
Thank
Smile.
you.
Okay, and then we will take a photo together with the oral presentation award, and maybe first shot with the oral presentation award 6 students. And then if you're still there, I think maybe everybody like turn on the camera together, and next session we will announce for the next host. Okay, so maybe stop showing the slide, and then you can see all participants together. Okay, so now it's Gary show. Nice to see you all. Okay, and thank you so much for staying together for 3 days. Okay, if anybody has a camera, maybe turn on the camera and then we take a shot together.
Together.
Okay. That's good. We see virtually, like, because now it's COVID pandemic, and like hope you enjoy. Okay, so maybe on my count, 1, 2, 3, smile. Okay, I think I heard some Photoshop. Okay, is it done? Or the organizer, would you please confirm me?
Maybe one more, please.
One more, okay.
One more.
Okay.
再来一次。
1, 2, 3. Okay, I think it's done. Okay. So we have two screen that organizer. I hope that you could like capture all the participants. And then that is the announcement for the next host for the next the third YSCRC that will be organized in 2022. So may I invite Professor Lam? Would you please present your slide? Okay. Okay, Professor, please.
Professor, please turn on your microphone.
Okay, again, I said Sawadee Krap. Yeah. Thank you for the organizer. Thank you, Professor Suwadi. Thank you for our President, Professor Sri. Okay, so thank you for the good organization for 2021 and set a very good example for 2022 that coming to Kuala Lumpur next year. Okay, so we welcome you to Kuala Lumpur, Malaysia next year. So this is the history, just for your memory. So we have 2019, okay, in Shenyang, China. And then, of course, now we have it a very great one at Bangkok, Thailand. And next year we will come to Kuala Lumpur. And you're all welcome to Malaysia, even though we will set it as an online conference. But why not? Yeah. So join next year, then we have a good feeling, then you will be physically in Malaysia very soon. Yeah, we will have a series of conference after this pandemic. Okay, so of course we will use back the same international scientific committee that successfully organized the first one and second one. Okay, of course we hope that the list of the scientific committee will be expanded with more support so that this conference will be bigger and bigger. We hope that because now we see that it's mostly Asians, we hope that by the coming time, we will have more participants outside the Asia to join us, because we set the conference this is an international symposium. Yeah. So I hope that all over the friends here, please spread the news to outside the world that this good conference is coming back again next year, and it will be in Malaysia. Okay, so for organizing committee, of course, I believe the list will be expanding. Okay, this is a short time, at the shortest time that I can get those who 100% will support to join and to organize this conference for next year. So at this moment, we have 6 universities from Malaysia to agree to join us together. Okay, sorry, it's 4 from Malaysia, 1 from Brunei and 1 from Holland to help us. Okay, so I hope that this can set a good example that this conference will step up from Asia. At least we have 1 organizing committee from Netherlands now. All right, so tentative events, I think Thailand this year set a very good example. We will most likely follow them. Okay, we will do online conference unless suddenly our pandemic drop very positive, then we will consider for the physical conference. At this moment, the Malaysian side, we set it as an online conference, right? So of course, we will have plenary lecturers. We will try to invite those good famous professors to give us enlightenment, okay, by giving plenary lectures. We will have workshops. We will have the best poster awards, best presenter award, like what we have it now. And of course, we will try to organize some special issues so that we will expose our good works, good reports to the worldwide international journal. For your information, the topic that we will focus on, first of all, we have characterization and pretreatment for the biomass and carbon resources. I think here is very famous with thermochemical conversions, biological conversions, electrochemical conversions, catalysts in conversion, so on and so forth. We also will talk about carbon materials, environmental remedies, or solution for the environmental issues that involve carbon resources. Last but not least will be the process engineering system, or we call process technologies, that from the macro point of view, that how can we encourage the carbon conversions. The date for the coming event is we tentatively set it mid-September 2022. Okay, I think most likely that time is a holiday for you. I'm not sure. We will do the survey again, but tentatively we will put it as a mid-September 2022. The fees, don't worry, because this will be online. We will make it as minimum as possible. Okay, I don't know how much yet. If we can get sponsor, it can be free of charge. I don't know. We cannot promise anything. So since we are very sincere to make it as wide, as big as we can, we really hope that we will get back the bigger support from you all. And from that, we really want to make it as minimum as we can. As we said this from the first conference in Shenyang, we say this conference is supposed to be for the young researcher, not to make money and so on. So again, I stress here, the fees will be as minimum as possible. If we get enough sponsorship, then we will make it free. Okay, the website will be announced soon. We will use the email list to send the invitation to you. Okay, so be ready. We will set up the email and the website, and then we will send it out soon. If you really miss, you're really afraid you miss this, please mark down my email. So my email is listed down there. Okay, you can screenshot or whatever, but there. So please drop me an email if you want me to update you about this event. Yeah. Last but not least, please welcome to next year in Kuala Lumpur. We will see you soon. Okay, thank you, Professor Suwadi.
Okay, thank you very much. I hope to see you again next time. See you all. So before we end off our session today, the organizer prepared some screen to share about Malaysia. So the organizer, would you please share slide? Share the link and the song as well. So we will end of this meeting with the song of the Malaysia. So that will be the next host. Okay. Okay, organizer, would you please share the screen? Okay, see you again next time and take care of yourself. Okay, bye-bye. So now it's time to say goodbye.
Okay,
Bye-bye,
bye-bye,
everybody.
bye-bye. See you.
Bye-bye.
See you.
See you.
See you next time.
Bye-bye.
Bye. See you next year. Bye.
See
Yes,
you.
yes.
เดี๋ยวรอให้แขกออกก่อนหมดเนาะแล้วเราเดี๋ยวค่อยเอาค่อยปิด